Okay, well, let's go ahead and get started. Yuri Kovalev and I are really delighted to welcome you to this parallel session on experimental relativity with radio astronomy. So we'll hear lots of different talks, across high resolution radio astronomy with VLBI and even touching on things like the cosmic microwave background. So thanks to all of you for joining, and really a special thanks to those who will be presenting today. So we'll hear 6 presentations, and then there's a partner session on Thursday that will have an additional 6 presentations. So I encourage you all to join that as well. So each talk that we'll have today, we'll have time for questions at the end. If you have follow-on questions, or if you want to note something during the talk, you can also use the Zoom chat. But I think we should treat this as fairly casual and collegial, as much of an in-person style as possible. So please, you're welcome to turn on your video, or you're welcome to unmute, and hopefully we can have some stimulating discussions. So each speaker, I'll give you a warning 5 minutes before the end of your talk. So if your talk is 20 minutes, I'll give you a warning at 15, and if it's 30, I'll give you a warning at 25. So our first speaker today is Maciek Rielgus, and he'll be telling us about the first polarized images of a black hole with the Event Horizon Telescope.
Hello, everyone. I'm absolutely delighted to talk to you about these results from the Event Horizon Telescope. First, let me maybe explain. I see this session is a space VLBI session, but the Earth is in space, hence all VLBI is space VLBI. So it makes perfect sense to present these results from the Event Horizon Telescope in this session. So I did put a couple of names here that you see. These are several people who contributed greatly to this aspect of work. I will be talking about how we got the data and how we performed imaging of the linear polarized component in M87. And then there will be another talk from Daniel Palumbo, who will give you details about what does it all of that mean from the theoretical point of view. Okay, so let's move on. So I said a couple of people were on the first slide, but of course it's a big effort from larger group. Event Horizon Telescope is a big collaboration, and we do need a large collaboration for the reason that within this collaboration we do everything from electronics, hardware, observations, data reduction, data processing, data analysis, all the way to the theoretical interpretation. So what you see here is not even, probably at the moment, not even a half of the entire collaboration. We do need a lot of people. We need to bring together people with expertise in very different aspects of all of this work. We take a holistic approach. Okay. This was our team of people. Now about our instrument, the Event Horizon Telescope. I do believe in this session there is absolutely no need to introduce the concept of VLBI. I see only amazing experts in the audience, so I will not do it. Nevertheless, let me just say a sentence or two about the EHT. So it is a global array of telescopes. They are not physically connected. They are located in very different parts of the globe. You can see here the progress of our hardware, of our array of telescopes. Everything I'm talking about today is based on 2017 observations, everything. But the observations from 2018 and 2021 are concluded. So we only expect to get better at it. We only expect to give better and more robust results in the future. However, everything today is only 2017. Okay, so there is a team, there's a telescope. Now, where do we point that telescope at? I will be talking about results on M87. M87 is this giant galaxy in the Virgo cluster, the first jet we ever saw about 100 years ago. And since then, we were slowly zooming in, trying to pin down the origin of this jet in the core of the galaxy. And only 2 years ago, we saw for the first time the resolved total intensity image of the feature at the origin of the jet. And we saw this donut, and we called that object there M87 with a star to distinguish it from the galaxy. So this is how things looked like 2 years ago. This is the results published 2 years ago, although this is after the most recent Marcel Grossman meeting. Nevertheless, it's kind of old at this point. It's 2 years old. In Poland, we would say it's as relevant now as last year's snow. That's the phrase we we would use. So I will not be talking about 2 years old results. I will be talking about 3 months old results, which is the linear polarization of this object. So we added to this total intensity image, we added this pattern that you see here, and I will try to explain how did we get that pattern and what do this hairy structure here what is that supposed to mean. So, well, I will start with this. This is a little animation showing you M87 as seen by ALMA over the Atacama Desert. Let me say that the size of the donut is quite exaggerated, of course, here. You can see how it changes, how the position changes during the night of observations. So you can see the frame of the image, how the yellow frame, how it is rotating, but you can also see the frame in which we observe, the frame of the polarized receivers. So as you see, there is a rotation between one and the other. So it is a little bit of headache, but it really means that we just have to do our bookkeeping right. On the other hand, it helps us to disentangle between the instrumental effects and the intrinsic source properties. So this is a linear polarization is a vector. We observe a vector. So there is this nice animation here, which is telling you what we would see if we only looked at polarization in particular direction, if we rotate our polarizer. So we need 2 polarizers. We need to have 2 components of this vector to recover all the information about linear polarization. Matter of fact, we actually have, well, we do need to observe 2 perpendicular polarized components at each of the stations, but it means, because interferometry deals with the correlation coefficients, it means that if we consider 2 telescopes, we have 4 correlation products that we can calculate between when each of them have 2 orthogonal polarized streams of data. And then by the magic of linear algebra, we can recover from this information, we can actually recover the full state of the electromagnetic, polarized electromagnetic field, meaning the full Stokes vector. So this is what we get through just algebraic operations. So this sounds simple. It's not. It's very difficult, actually. VLBI is always difficult. Polarized, polarimetric VLBI is quite a headache. But, well, one of the parts of this headache is that you measure components in the Fourier domain. So to get to the image, you need to calculate, reverse the Fourier transform from the sparsely sampled data. But before you take an attempt at that, you already can say something about the source, just looking at the data. So this is not biased by the imaging problems with the imaging algorithm. So you can see here 4 nights, we observed M87 for 4 nights, and you can see a fractional polarization in the Fourier domain here. So don't be alarmed that the fractional component can be higher than 1. That is the case in the Fourier domain. We can already say something about the object from that. We know that it's compact because we did the total intensity imaging. We know that it's weakly polarized, well, because it's kind of bluish, not reddish on this scale, meaning the polarization fractions are rather low. And we can also see already that there is some signature of evolution between the days. So not only we see the source, we see that the source is probably changing between the days, which is quite fascinating. So if we know that, if we look at the data, we can make a first attempt at imaging. The first attempt was 2 years ago in 2019. We took 3 algorithms that we had at our disposal at this point, and we tried to ask them what is the image of this source. So you can see 3 columns here: total intensity, we knew what to expect there from previous experience; linear polarimetry, we had no idea what to expect or little idea. And you can also see last column, this is the main source of a headache with the calibration, the leakage, which is basically a crosstalk between orthogonal polarized receivers. So how much polarization leaks between them. I will not give any details about that. All we want to see that these independent methods give us similar pictures here, so similar points on the complex plane, and you see they do. So this is a huge boost of a confidence that we are indeed doing the right thing. We're not limited by the calibration problems. So this is a bunch of happy faces after seeing that for the first time, comparing three algorithms and seeing that they are consistent. It is extremely weird to look at pictures like that. So many people crowded in the single room, nobody wearing masks, but well, that is how the world used to look like 2 years ago. You can also see that using my amazing Photoshop skills, I added one person here. This is Sarah Izaun, who is an important contributor to this work, but she didn't make it to this particular image, to this particular photograph. So I smoothly added her here. Right, we have to assure ourselves that we are indeed seeing the right thing. So we perform a whole bunch of different tests to enable this assurance. I will not be talking about 10% of those. I will be talking about 1% of those tests. So one test we can do is we can compare results of the VLBI with ALMA. EHT is a mess because all those telescopes were never built to communicate with one another. We have to teach them to talk to one another through these complicated data calibration procedures. However, ALMA is a marvel of technology, amazingly sensitive telescopes that were designed to work as a single interferometric instrument. So, of course, ALMA doesn't have the resolution of VLBI. However, we can compare the total compact polarized flux between ALMA and VLBI. And we can do it for multiple sources because Event Horizon Telescope did observe multiple sources that most of them are not published. You can see here that the polarized components, Q and U components of the linear polarization vector, agree very well between the observation of ALMA and VLBI observations, another boost of confidence. A quick comment is that, well, only 3C279 and M87 were published from this set of sources. Some of them are really interesting, so I encourage you to really look forward and carefully look at the news next week, maybe, or maybe sometime in the future, because there may be another of these interesting sources published very, very shortly. So these were very simple tests. Now for the more sophisticated tests. How about we take synthetic data sets, push it through our algorithm, and see if we can recover the true structure. We use a couple of different models of the sources in our synthetic data sets. Some of them come from the general relativistic magnetohydrodynamic simulations. They can look like the upper row in linear polarization components. Some of them are just geometric components, just a bunch of rings with imposed structure of linear polarization. So let's choose one. I'll choose the bottom right one, and let's ask now 5 algorithms. We stepped up our game, and now we have 5 algorithms, not 3, to independently perform the reconstruction. So you can see how well they are doing with reconstructing the synthetic data that should look like that. You can see some of them make mistakes, but usually they get bulk of the structure right. So the idea is, well, if those are independent algorithms that make independent choices about what they do, how about we just average the result? Meaning that if there is one algorithm that wants to do particularly weird thing, let's say maybe there is an excess of polarization here seen in LPCAL algorithm, if we average it down, we ensure that we only see something that all algorithms are really seeing. So that's what we did. So this is one of the data sets, April 11th, done calculated, reconstructed with 5 different algorithms. And it's beautiful consistency. There are details that are different, but you can see that the magnitude of polarization is consistent. The location of the polarized component is consistent. So overall, it is quite satisfying. This is just one day. Now we can do several days. We have 4 nights of observing of M87. We perform this reconstruction. Now there are 2 rows here. These are just 2 different styles of display of these results. So we use the bottom row mostly for the reasons of public outreach, because they are really, really beautiful. but the amount of information should be exactly the same in both of these methods of displaying this information. One interesting thing you can take a look at is that there is a shift of the polarized component counterclockwise between data sets from April 5th and 6th and the ones taken several days later on April 10th and 11th. I will skip that for the sake of time. This is an additional test of the robustness of our algorithm. And this is a continuation of that previous one. I will only point one thing in this slide. I would like you to take a look here at this plot of position angle versus the magnitude of the polarized flux density. And notice that there is a shift in position angle between April 5th and 11th. So this is a quantification of that thing that I mentioned in the previous slide about there being a shift in the polarized component. There is a counterclockwise motion of this polarized component. This motion has a direction consistent with the motion that we saw in a position angle of the total intensity component. And well, I said I wouldn't spend time on this slide, but I ended up doing that. The message of this slide was really that, the intrinsic structure of the source is strongly dominant over uncertainties that we have either from the leakage uncertainties or from the statistical errors. So the thickness of these lines would correspond to the uncertainties between reconstructions, between different leakage parameters that we solved for, and to the statistical uncertainties. So the fact that they are thick, but they are not all over the place is telling you that the source structure is dominating.
Now, 5 minutes left, including questions.
That's plenty of time. Including. Okay, I'll be quick. Okay, so now we have images, we have reconstructions. We need a couple of ways to quantify the geometric information in those. So couple of ways to do that, the ways we used in our work of the Event Horizon Telescope. We can calculate the net polarization, which is just coherently averaged polarization, meaning it can add destructively. We can calculate mean polarization, where we add just the absolute values of the polarization, meaning it cannot add destructively. You can see when we find the different values, but you can also see that it's always telling you that the source is weakly polarized. Here you can see that 10% is the upper limit. Finally, there is this very fancy parameter that we call beta 2. It was introduced by the next speaker, Daniel Palumbo, in work from the last year. I will not explain that in detail. I will just show a quick image indicating what it's telling us about. It's telling us about the geometry of this polarized component. Are those polarization tick marks radial, azimuthal, or are they somehow twisty? Okay, and a final thing, so we applied to the reconstructions of the images. We look at different bands, frequency bands. We look at different days. We look at 5 different methods. And as you see here, we find consistent results for those geometric parameters, meaning we can use that as measurement made on our source. One final thing is the EVPA. This is the averaged position angle of the electric vector. You can also see consistency between the methods, but you can also see a shift between the days. So this is exemplifying this effect that there is motion in this image between the different sets recorded on different dates. And just the summary, I'll extremely quickly go through some of those points. It's the first time that we actually see something like that. We see the polarized component so close to the event horizon. It is a challenge to get there with the data sets. We have many ways to ensure the robustness of these results, and we see variability across the days. And one final comment, the future. Well, we have 2018, 2021 observations. We didn't publish on circular polarization, which we may do if we are able to. And future data sets will be better equipped to calculate robustly things like rotation measure. So that will be, I imagine, extremely exciting. Okay, thanks.
Thank you very much, Maciek. So please feel free to raise your hand in Zoom or just unmute. I see Yuri has his hand up. Go for it.
Yes, thank you. Okay, I always had how to put it properly, worries or reservations regarding averaging images which you got from different algorithms, because apparently one algorithm is better than another, but I'm not going to debate it right now. I will put it in the form of a question. So you have discussed today that so you've averaged like 4 or 5 algorithms, right, for polarization. So tell me, if you do not average, but if you use a median, apparently when you use median, first of all, the result might be a little bit different. But I mean, I don't ask you to show me that because probably you don't have it. But tell me, which algorithm gives you an output, an outcome, an image which is the farthest from the average or the farthest from the median?
Oh, that's a good question to which I don't know the answer.
Seriously, most probably you do, but you don't want to tell it.
The median is obviously LPCal.
Say it again, Andrei.
The median is obviously LPCal. You see it here.
So, but Yuri, I will try to deflect your question just a little bit, just a tiny deflection to this slide and this figure, where you can see those multiple algorithms and how much do they differ when we actually try to quantify it, and when to get a number that we can use for the theoretical to compare with theoretical predictions. So you can see that we really take the range that is broad enough to accommodate all of them, but they are not extremely different. It's not the case that you will get 5% polarization with one algorithm and one with the other algorithm. Well, did I deflect your question successfully?
I still don't know which algorithm is the worst one.
Well, yeah, I honestly don't know. I'm sure there is one that is farther from the mean than others, but I cannot tell you which one is that.
Yeah,
Can you make a comment?
Please, yeah.
Well, if you look at these ranges, it tells you immediately that all these algorithms essentially perform pretty homogeneously. And in fact, if you look at the decision to average, it's probably just not quite to say political decision, but just a decision to produce a consensus image, which will not tell that this is LPCal image or Paul Solve image and so on. But it's like our old seminarists in university said, you cannot cheat on the nature. So this algorithm do enormous work and they come up to very consistent results. I wouldn't say one is worse or better because they have some internal biases, but they're very small in comparison to overall outcome. Sorry.
Yeah, of course, all of that, all of that can be debated in a sense. Well, in a sense that you can debate pretty much anything, and by averaging that and using the averaged image, you can actually make it farther away from the data than any individual image. This is a possibility. So there are arguments to show 5 images, and that's why we do show 5 images. We show all of those, right? But well, for the at very least presentation purposes, it's good to have one image. It's terrible to go around with a huge table by different by different day and by different algorithm, because it's difficult for people to parse hundreds of images. But one should think about it as a distribution, really. One shouldn't think about it as, well, this is the image, this is the truth.
Great. So we need to move on, but the next talk is in a similar vein. So maybe we can continue some of this discussion.
Thank you again.
Thanks, Maciek. So next up, we have a presentation from Daniel Palumbo on dynamically important magnetic fields at the M87 horizon.
All right, let's see if I can get this to look right. Can you all see this?
Yep, looks
great. Thank you, Maciek, for an awesome talk. My name is Daniel Palumbo. I'm a PhD student in astronomy at Harvard University, and I'm here on behalf of the Event Horizon Telescope collaboration to tell you about the theoretical interpretation of the images that Maciek just showed you. So this can be found in M87 paper 8, and like any EHT output, it's the result of decades of hard work by hundreds of people, but this particular analysis was helmed by the paper 8 writing team, which is enumerated here. It was coordinated by Andrew Shale, who I think is on the call. Hi, Andrew. Jason Dexter, and Monica Moskobrodska, with additional work by Charles Gamy, Alejandra Jimenez Rosales, myself, Ben Prather, Angela Ricarte, and George Wong. So paper 8 has a wealth of sort of simple and compelling arguments and comparisons to simple toy models, as well as a very detailed comparison to general relativistic magnetohydrodynamic simulations. The focus of my talk will be the latter of those two, both because it's the bulk of the paper and the core of the result, which is that M87 looks like a magnetically arrested disk. With that in mind, a little bit of zoology. So for low luminosity AGN, like M87, the accretion flows of interest can generally be sorted into two states. There's standard and normal evolution, which has weaker fields that tend to just go with the flow and end up looking mostly toroidal, essentially spiraling slowly into the black hole in the geometry that you would sort of imagine. And there's magnetically arrested disks, which have strong, dynamically important fields that are in particular strong enough to balance the inward ram pressure of the gas in the disk, which is diagrammed here in Ramesh's original work proposing this state. And these fields pile up on the horizon and essentially produce strong radial and vertical components that it's a very different geometry than what you expect for sanes. And so it would be very nice to be able to tell these apart from images, because that would tell us something about the way black hole accretion systems form and evolve over eons, and it would tell us that we're doing something right in our simulations, which produce these states naturally. However, at the EHT resolution, total intensity isn't enough. So I've got 3 models up here. This is from our first paper in the total intensity paper series, just making the point that whether you have a retrograde high spin sane or a 0 spin sane or a prograde high spin MAD, they really are capable of looking very similar to the observed image, which in one sense is good news, right? It means that we're capable of sitting down and writing down models and running our computers and generating things that look like nature, at least the way nature looks to our blurry instrument. But on the other hand, we are not yet capable of telling apart MAD and sane, despite the fact that these have qualitatively very different dynamics near the horizon. That is, until you add in polarization. So we fortunately have a direct handle on the underlying magnetic field geometry by way of synchrotron radiation, which is dominant at the 230 gigahertz observing frequency of the EHT. So in principle, we could just look at the observed image that Maciek just showed, and because synchrotron emission is essentially polarized 90 degrees off from the underlying magnetic field direction, we could just rotate by 90 degrees and we would get the projection of the magnetic field onto the sky. In practice, this is not possible because of Faraday effects, particularly Faraday rotation. When a ray of light that we've observed is passing through a magnetized plasma, it's going to rotate. Essentially, the electric vector position angle, or EVPA, is going to rotate in a way that's proportional to the density of electrons, the magnetic field strength, and to the wavelength squared. And internally to the flow, where the stuff actually is and the magnetic fields are strong relative to the vacuum, this rotation can be quite large, to the point that you would expect it to wipe out most fine scale magnetic field structure at our resolution. However, externally to the flow, you might imagine that there could be some bubble of magnetized plasma that the image passes through, or some net effect on its way to us that would coherently rotate all of the ticks in the image. So it's basically grabbing every polarization vector and rotating it by the same amount. And so an analysis led by Chiriaco Gotti, along with the rest of the collaboration, released alongside our collaboration papers on polarization, tried to disentangle these effects and got a very nice answer, which is that the external screen is likely small relative to the internal rotation. This is very good news, because if we're going to do a comparison to GRMHD simulations, our hope, if we've done our homework, is that our GRMHD simulations are capable of self-consistently modeling all of the internal rotation. And so we can compare apples to apples as long as the external rotation is small enough, and 10 degrees is small enough that we can essentially compare apples to apples. With that in mind, with this analysis of the Faraday effects in hand, our task is to interpret the images from paper 7 in the context of a very large library of snapshots from GRMHD simulations. And of course, we'll have to blur these snapshots to the HD resolution if we're going to be doing any comparisons in the image domain. It goes without saying that essentially any inference we draw from this comparison is going to have a very strong prior. And that prior is that the GRMHD library is a good description of the underlying accretion flow. Given that prior, we can make whatever strong statements we see are evidenced by the data, or supported by it. Maciek already stepped through most of these image metrics, so I will just sweep through them mostly very, very quickly. There's the integrated linear polarization fraction, the integrated circular polarization fraction, which is quite low for MD7, and there's the pixel-wise average fractional polarization, which is essentially a measure of how polarized resolved features are in this image. And finally, there's this azimuthal symmetry parameter, which, as Maciek said, was first sort of written down in a paper I wrote with George Walling and Ben Prather in 2020, which strives to essentially project out various aspects of the variation of the polarization over azimuthal angle. Here, that angle is var phi. There's a few ways to think about this. I think the simplest is to think of it as a Fourier transform of the polarization with respect to this image azimuthal angle var phi, where modes are indexed by m, and all m is telling you is how many times the EVPA tick rotates as you go about var phi. So for example, for m0, here in the center of this grid, it rotates 0 times. For m equals 2, it rotates twice, and this corresponds to the rotationally symmetric mode. Now this coefficient scales with the fractional polarization because it's proportional to p and ultimately normalized by the total Stokes I flux. It's defined in terms of a specified annulus, but for our purposes, we just use the whole image because we're not trying to chop out like big jet features or anything. And so we're going to be focusing even just a priori on m equals 2 because it's capturing almost by construction the a coefficient that is tied to the axisymmetry of the underlying magnetic fields. These are complex coefficients, and so their phase is important. It tells us essentially the 0 position of the northmost EVPA tick, but more generally, it tells us the overall pattern of the spiral, which here has a nice connection to that cartoon picture of the accretion states that we mentioned earlier. We might imagine that for sanes which have more toroidal fields in this cartoon picture, we can generate the EVPA by just thinking, oh, what's 90 degrees off from an azimuthal field everywhere? And the answer is something that's radial. Similarly for MADS, if it has stronger radial or vertical fields or some combination of the two, it would end up having EVPA that's more like a circle in the top right or more like one of these spirals in the bottom right. Of course, everything is more complicated in reality, and spin has a huge effect on phase, likely due to torquing up the fields, the fluid velocity and thus the fields that are dragged with them near the hole. So you end up getting more radial EVPA as spin gets higher. This was identified even back in 2020 with the original paper with George and Ben. But all of that's holistically contained in the analysis of the GRMHD. So with all of these tools in hand, we're going to compute these values for the 72,000 images in this GRMHD library and essentially score sets of GRMHD parameters, which are MAD or sane, spin, inclination, and the electron heating prescription as encoded by R low and R high. These are worked out by Monika Baska-Brodska, and essentially do a tune whether your emission is mostly in the disk or mostly in the jet. It's a way to generate different morphologies just by changing what your emission region is. We're going to generate all of these image metrics and score simulation parameters by essentially how many snapshots they're capable of creating that actually fit the data by falling within those ranges that that Maciek presented earlier. And so the first thing that falls out is that it certainly looks like MD7 is significantly depolarized. And this is immediately obvious just from looking at the image itself. There's this bright southeastern component with essentially no polarized intensity in it. Clearly, at our beam scale, there's significant depolarization happening. And that essentially comes from large Faraday rotation depths across the image, where the variance within a beam is going to be significantly more than 2 pi. So you're scrambling below the beam scale. It's not terribly surprising that we're still capable of seeing a beautiful spiral pattern. It just means that some imprint of the magnetic field is surviving. There's a bulk pattern that survives the large rotation depth, or we're seeing an imprint from a shallow Faraday depth into the material. So it doesn't forbid this nice pattern. It just means that we're going to see low polarization magnitudes overall. Speaking of which, it has relatively modest net linear and circular polarization. All this really knocks out are some prograde sane models, which have almost zero net linear polarization. But most other types of GRMHD are capable of producing snapshots with roughly this degree of net polarization. The PWP mode, this m equals 2 mode, is very constraining and indeed favors MAD for some subtle reasons. The beta 2 amplitude is actually not particularly constraining, though it certainly looks so in this figure for moments I will show you in a moment. But this phase is actually quite constraining because it is able to kick out this dark orange histogram, which corresponds to retrograde sanes. And this bundle that's at about minus 45 degrees in beta 2 phase, these are retrograde high spin sanes, which are otherwise miraculously good at looking like the EHT image. And so being able to exclude them is important to our conclusion that M87 is likely a MAD. However, this relies on an overall or an absolute sense of the EVPA. And so the fact that we can conclude that the external screen is small is important to this conclusion. And so if for some reason we thought the external screen was quite large, this phase would be washed out and would be too uncertain to use. So this is yet another reason, forward-looking, this is the space session, why higher frequency observations that might only be enabled by space would be very exciting for M87 polarimetry. And so just a note on this beta 2 amplitude, because we're looking down at an roughly axisymmetric system, we're going to see things that look rotationally symmetric. That's why the beta 2 mode is informative, but it means that whatever polarized structure we see, it's going to be projected largely into the beta 2 mode. And so the amplitude is going to be mostly degenerate with the average linear polarization. So much the same information is encoded in these two quantities, but the phase of the beta 2 is unique. It's really the only image metric we've posed here that is sensitive to the absolute EVPA, and it does so in a way that is quite physically motivated. So that's why it's so informative. And so this has some, well, regardless of how we score, and there's two scoring methods we used. One, we either demand that every GRMHD parameter set be capable of producing snapshots that simultaneously fall within the data ranges of every image metric, or there's this more smooth joint scoring method where essentially for each image metric we form a probability of success for each GRMHD parameter set given by the fraction of snapshots that fit the data range, and then we multiply them together to generate a sort of pseudo likelihood. And no matter how you slice it, you get that MADs are favored. However, this difference in scoring methods does drastically alter the distribution over the electron heating parameters. So R low and R high slosh around, and as do the spin and the detailed split among the sane models. And so what this tells us is that we should be cautious when inferring anything about the heating parameters or about spin. But nonetheless, we're comfortable saying that MADs are significantly favored. And so once we tighten our set of believable GRMHD models, that means we can tighten our constraints on the accretion rate that is predicted by these models. And so we tighten this by about 2 orders of magnitude. The jet power constraint is still rather flat. But I do want to maybe not hedge here, but at least give some hope for the future, which is that we are cautious around spin now because we're seeing very small snapshots of the flow. We're seeing essentially 2 moments of time, 2 days at the beginning of the week and 2 days at the end. And we use that to build a range of parameters. And so this is mostly visible in the beta 2 phase. These things are capable of wandering around significantly. Oh, sorry, am I hearing Michael unmute? Am I running on time?
I didn't unmute. You have about 5.5 minutes left.
Okay, great, perfect. That's exactly what I mean. Yeah, so the beta 2 phase wanders around quite a lot for MADs in particular. And as I mentioned earlier, there is a spin signature here. So higher cadence observations and higher frequency observations that improve our certainty in what the mean beta 2 phase is would start to give us a real handle on spin, even neglecting all of the beautiful symmetries in polarization and more generally in this system that will become evident with space field EI. So even if you don't even if you aren't terribly clever, you can still get a handle on the spin magnitude just by improving your instruments, which is exciting for the future. And so just to conclude, despite strong evidence for very strong internal Faraday rotation, there is an indelible imprint of magnetic fields on the image. It's this beautiful spiral pattern that has somehow made it through a strong internal Faraday rotation, and that alone is telling us a great deal about the accretion system. And given evidence for only weak external Faraday rotation, a screen that is not too significantly altering the absolute EVPA, MADS are strongly favored by EHT images of M87, particularly by this beta 2 phase and by the average linear polarization fraction. I think the future is bright. The Faraday rotation it's a lambda squared effect, and going to higher frequency will help a great deal there, and that will also give us higher resolution, and that will be addressed both by the NGHT and also by space, where there is no intrinsic atmospheric limit on our observing frequency. And of course, higher cadence images will tell us about all of the exciting dynamics here, and also give us a better sense of what the mean values of some of these parameters are in some wildly varying systems that are sort of debatably at quiescence. So I hope this informs the discussions of space that will happen in this session, and thank you for your time.
Great. Thanks so much, Daniel. Any questions for Daniel?
I can't see the participants list, so someone else may need to call on people.
I'll call on people. Yuri,
okay, great.
Did you have one, or?
Yeah, I do have a question, but I just want to give other people also a chance to ask. So I don't know if I should wait.
No, go ahead and lead off.
Okay, so Daniel, so regarding your second bullet, I actually had this question from the very beginning of your talk. So given the evidence for only weak external Faraday rotation, what happens if this evidence is wrong?
Right, so essentially what happens is the beta 2 phase constraint widens to, let's imagine we have no phase information, right? So the beta 2 phase constraint becomes minus 180 to 180. We lose all information there. And the punchline is that MADS are strongly favored, but probably some retrograde sains live on, probably retrograde high spin sains.
Okay, thank you.
I have a question. So my question is, there's this model down select, you're left with some that are favored. What's a testable prediction from those models? So not just that the system is mad, but something where is there some clear prediction where we'll go look in future years and see something that we haven't seen yet?
Right, so I think this comes from essentially a measure of what is the autocorrelation of these parameters, right? If we were to go look over and over and over again, we would expect things like the beta 2 amplitude to shift around not too much. The beta 2 phase could shift wildly about some mean. We'll see occasional flares in the fractional polarization. I think it would be very worrying if we ever saw the imaginary part of beta 2 flip. That would mean that we had done something terribly wrong, or that there was an external screen ruining things, because you would never expect that to flip sign. So to me, that's the sort of strongest test of whether we actually understand the external screen, is if later years flip the imaginary part of beta 2.
Mm-hmm. Okay. Okay, well, with that, we should probably move on, but thanks again, Daniel, for the very nice talk. And next up, we have Alexandru Lupsaska, who's going to tell us about the black hole photon ring. And I'll give you a warning 25 minutes in.
Thank you, Michael, and thank you for the invitation to speak at this conference. Thank you to the organizers. So I'd like to tell you about the black hole photon ring, which I think perhaps many of you have already heard about, but I'll focus half of my talk on the theory and then briefly describe why I think it's interesting and how I wish we could go forward and, using radio astronomy from space, as this session is called, measure properties of the ring and learn about gravity using that. So to set the stage, of course, this is the image of M87, which is by now familiar to everybody on this call, I'm sure. And it's absolutely remarkable that the Event Horizon Telescope was able to take this image. It's the very first real picture of an actual black hole up there in the sky. And of course, if you were there the press conference when it was first released, the first two questions from the journalists were, well, why is it so blurry? And it is an amazing achievement, but we have to look to the future now and think about all the exciting new technologies we're going to have and how they'll let us resolve this image better and better and better, and start asking what are we going to learn specifically as that happens. So our best guess for what the actual image looks like, which is based on GRMHD, General Relativistic Magnetohydrodynamics, is that it should look something like this, with the previous image a blurred version of this because of the Event Horizon Telescope's present resolution. And so this is our best guess currently as to what the image of M87 should look like. And there's a number of striking features in this image. So the first one is, let me know that there's a much darker patch here, which sits inside a bright ring. So today I'll tell you about this very bright photon ring, but let me know that this dark patch is actually in this model is the image of the event horizon itself. And I urge you to listen to Andrew Chale's talk on Thursday in the same session where he'll be discussing what this means theoretically and what we can do with it. But I'll be focusing on this very bright ring of light, which is probably the most prominent feature on this image. And it's very striking, especially because it's present in all the simulated images that we have of the source in the HD data bank. So there are many, many GRMHD simulated images of M87, and they all present this feature. So how can that be? As you vary the source model, you still see this ring. And so the 3 points I want to convey in this talk are, first, what is the origin of this ring of light? Second, how we can better resolve it. And third, why that's interesting and what we can learn from it. And just to give away the punchline, the reason this ring of light is present all the time in all the images that we look at is that it's a universal effect of general relativity. That is to say, it's matter independent. It doesn't depend too much or hardly at all on the details of the source. It just follows from the lensing properties of a Kerr black hole. And not only that, but this photon ring actually has an intricate substructure made of many subrings. And the subring structure is entirely governed by 3 critical parameters, gamma, delta, tau, which I'll describe and follow purely from general relativity and the Kerr metric. Now, this photon ring is clearly visible in the image. It's the most striking, to me at least, feature. But it's also very striking in Fourier space, where we actually take measurements with the Event Horizon Telescope or other interferometers. And what I'll explain is this beautiful idea that actually by going to long interferometric baselines, we ought to be able to isolate the photon ring. And that will require us going to space, which I think is the most exciting development that I'm looking forward to in the field of black hole imaging over the next few decades. And I think the shape and what we can learn from it, well, there are many things, but maybe one of the least ambitious ones that we should, it's very ambitious to aim for in our lifetime, but is actually doable, I hope, is to measure the precise shape of the photon ring, which is predicted by general relativity to be an ellipse. And that prediction is remarkably insensitive to the astronomical source profile and could be used as a very stringent test of strong field general relativity using a space-based interferometer. Okay, let me just quickly state that following the release of the image of M87 in April 2019, there has been an explosion of papers on the topic of the photon ring. I could not list them all. I just listed a few, like these 3 that I'll essentially be reviewing in this talk. But let me mention that there will be other aspects of the photon ring described in this session on Thursday. So Mina Himwich will discuss the polarization of the photon ring. As I mentioned, Andrew Chale will talk about the photon ring in conjunction with that dark patch, which is the image of the event horizon or the inner shadow. And let me also mention that Zachary Gellis will have a talk on one of his many papers. He's a very brilliant undergrad, someone to look for, lots of great things coming from him. And another thing I want to mention here is that this topic is growing to include numerical simulations and theoretical calculations and even mathematics papers, and it's moving into high energy theory. So I think there's lots of exciting connections between experiment and theory to explore. Now, my own involvement with the subjects began with this paper that was led by Michael and also involved many of the people here on this call. Then I wrote a couple of follow-ups with Sam Gralla with many, many technical details. I'm listing the references here, and everything I'll be telling you can be looked up in here. So what's the story in brief? Well, in brief, it turns out that if you have a black hole, there's the event horizon from which light cannot escape. So everything that crosses in here is stuck in here forever. But there's a region outside the event horizon, which is drawn here, which is now known as the photon shell, in which gravity is so strong that light rays can be deflected so much that they actually orbit the black hole, and in principle can circumnavigate it multiple times. But of course, they're not trapped yet, so they can still escape and reach us. And there's this beautiful animation on the, there's an interactive applet on Leo Stein's website that you can play with. This is a screenshot from that applet that shows you the bound orbits in this photon shell that just go around the black hole multiple times. You can play with them. And there are three critical parameters that follow from the Kerr metric, so just Einstein's general relativity, that completely characterize the properties of these orbits. And the first two are very simple. They're called delta and tau, and they're just the azimuth swept, so how much angle phi was swept by a photon as it did one orbit, and tau is the time lapse incurred in a half orbit. And here by an orbit or a half orbit, what I mean is that these light rays, they stay at fixed radius, Bohr-Lindquist radius, but they oscillate in theta and they bounce up and down in the geometry. And so one full orbit is going from the bottom to the top and back, and one half orbit is just crossing the shell once. So delta and tau are just how much the light rotates and how long it takes for it to just go from the bottom to the top once. And these are functions of the black hole parameters, which is important, the mass and the spin, and also the radius in the photon shell. Let me also mention that as the black hole spins down, as you go towards Schwarzschild, this photon shell shrinks to a single sphere, which is at r equals 3m, outside the horizon at r equals 2m. And as the black hole spins up, the horizon moves in until it's eventually at r equals m, but the photon shell thickens until it goes from m to 4m for an extremal black hole. Okay, so these are two of the critical parameters. They're the easy ones. And the last one is the Lyapunov exponent, which characterizes the instability of nearly bound orbits, so not the exactly bound ones. And so for that, we have to talk about deviations from being perfectly bound. Now, these orbits are unstably bound. And so if you take a light ray that would have its momentum aimed just right so that it stays in the photon shell and orbits around, but if you just bump it a little bit to the side, what you'll find is that it'll rapidly leave the photon shell. And in fact, its radial coordinate, the distance from where it was supposed to orbit, will grow exponentially in the number of half orbits n. And this Lyapunov exponent gamma just controls, it governs the rate of instability, how fast this exponential deviation in the radius happens. And you can compute it from studying the geodesic deviation equation. So this is the third and last critical exponent. It's also a function of the spin of the black hole and its mass and the photon shell radius. Okay, so now that we've described properties of these rays in the photon shell, I want to start to move us to images of these light rays, which will turn out to be the photon ring. And so the one key concept here is that of a critical curve, which appears in the image plane of a distant observer. So if you're a distant observer looking at the black hole, and you point your telescope to the black hole, and you ask, okay, if I send a light ray back towards the black hole, what happens to it? Well, if you send the light ray very far away, maybe it gets deflected a little bit by the black hole, but it escapes back out to infinity. But if you send a light ray towards the black hole, it gets sucked into the event horizon and gets stopped there forever. The boundary between these two regions, the region of photon capture in here and the region of photon escape in here, is this critical curve. And so what happens if you aim a light ray exactly on this critical curve? Well, it ends up asymptoting to one of these bound orbits. So it's captured by the black hole and orbits it forever, but outside the event horizon. And what's interesting, there's a lot to say about this. I'll just point out one thing, which is that depending on the angle around the image that you point to, the photon ends up orbiting a different radius. So looking around the black hole is not looking around it in the geometry, but looking deeper or closer from the black hole. And that's really the warped geometry of space-time brought to life on your screen. And for the purpose of understanding the photon ring, the key point is to look at near critical rays, which are not exactly on the critical curve, but aim slightly inside of it or slightly outside of it at some perpendicular distance d. And these light rays will orbit the black hole many times before they eventually escape if d is positive, or fall into the black hole if d is negative. So these light rays are very important because their existence implies that since light rays near this curve can go around the black hole multiple times, that means that a light source, a single light source around the black hole, can connect to an observer, to a single observer along multiple rays. So you can see multiple images of the same source if you look near the critical curve. And so just to give you one slide to explain how this works, let's take the simplest example where you look from the spin axis of a black hole at an equatorial disk. And what you'll see is there will be some direct light that comes at you straight up, this n equals 0 light ray, but then there will be a light ray that's actually shot down, does one extra half orbit around the black hole before reaching you, that's n equals 1. Then there will be a light ray that does 2 half orbits before reaching you, and then in principle there will be n equals 3, 4, so on and so forth. And what's nice is that in the high n regime, so for n greater than 1, these successive lensed images of the source are simply related to each other. So if you assume that this is your mth image of the disk, the m plus 1th in this simple case is obtained just by rotating the image by an amount delta, time delaying by an amount tau, because that's how much the light rays rotated and how long it took for them to do the additional half orbit. And then the key thing is that the image is demagnified or squeezed in closer to the critical curve by an amount e to the minus gamma. Okay, so that's basically the key to understanding lensing by curved black holes. And in the general case, it's a little bit more complicated, but roughly it works the same way, just with messier equations. Now, to tie it all together, let's imagine that we were ray tracing to produce simulated images like the ones I showed you at the very beginning of the talk from GRMHD. So what do? We want to figure out the intensity of each pixel on the image, I of alpha beta. So we take a light ray, we shoot it back, evolving it using the null geodesic equation towards the black hole. And at some point, it passes through some matter source that shines light. And then we use the equations of radiative transfer, which tell us how many photons to load onto the ray as it crosses through the matter. It's basically the number is proportional to the emissivity of the source. In principle, you can lose photons if the matter absorbs it. I'm going to neglect this. And for the frequencies at which we observe the source, this is a decent assumption, as I'll show you soon. And if you do this, well, there's a simple, very simple calculation, which is that I told you that if you want to do n turns around the image, you have to approach the critical curve. So the distance from the critical curve has to decrease. And I told you that images labeled by n appear exponentially close. So that's this relation. You can invert it and you can find that in order to do n turns, you have to aim logarithmically close to the critical curve. And so what that means is that if you look at pixels very close to the critical curve on your screen, the light rays that you're shooting back will actually orbit more and more around the black hole. And this implies that they'll pick up more and more light because they'll pass through this emission region in the photon shell multiple times. Roughly, for n turns, you'll have roughly n times the intensity. And so the photon ring is just the brightness enhancement that you get on your screen, this bump in the intensity that arises because of these critical orbits that pick up the emission multiple times. And in the real world, there are no light rays that go around infinitely many times because they eventually get absorbed. But in simulations, we find that for the parameters that we believe hold true for M87, you can go around multiple times before getting absorbed. Of course, at higher frequencies, you can go more times. And just to cement the discussion, let me show this video that was professionally produced, which I quite like. So basically, if you look at a black hole, what you'll see are light rays that are emitted from all the stuff around it, and they just come at you more or less directly, maybe with some weak deflection. And that n equals 0 image just shows you the source as it is, or weakly lensed. But additionally, on top of that, you also see n equals 1 light rays that do one extra half orbit. So they do a U-turn around the black hole. They're deflected by its gravity and reach you. And because they have to be aimed just right in the photon shell to do this, they appear lensed in a particular ring-like region on your screen. And then there are these n equals 2 orbits, which are even more strongly lensed, but you have to aim even better for that to happen. And so they end up lensed into an even tinier ring. And so the total image that you see is a superposition of all these images, the n equals 0 background, the direct emission, and on top of that, the n equals 1 emission, which is this very noticeable ring, and then inside of it, there's an n equals 2, n equals 3 ring, so on and so forth. So I think that's absolutely a fascinating, crazy structure. It's amazing that black holes really work like this according to general relativity, and I think it's unbelievable that we're now thinking about getting signals that confirm this. I think this is hugely exciting. And I'm certainly spending most of my time thinking about this. So this story has been confirmed by state-of-the-art numerical simulations. Here I'm showing some that were run by George Wong, then a student in Gami's group in Illinois, now soon to start his postdoc at Princeton. And so what I'm showing you are cross-sections of this image, horizontal and vertical. They're shown in blue and red here. And you can see that there's this shoulder, the n equals 0 emission, and then on top of that, there's the n equals 1 ring, and then there's an n equals 2. And if you zoom in on the ring here, in these panels, these zoom in panels, you can actually see that the n equals 0 image has the n equals 1, n equals 2, n equals 3, and I think George checked up at n equals 6 in this particular simulation. So this is a theoretical effect that we understand analytically, and it's confirmed by state-of-the-art numerical simulations. And so, obviously now we would like to see it experimentally in the real world. And so that's kind of what I'm going to move towards, but let me just summarize everything that I've told you. This was the theory part. So it's a prediction of general relativity that embedded within an image of a black hole, there should lie a thin photon ring, which is composed, in fact, of a sequence of self-similar subrings, with each subring a lensed image of the main emission, indexed by the number n of half orbits that was executed around the black hole. And this structure of subrings arises from Kerr lensing. And so it's completely characterized by properties of the Kerr metric in general relativity, and in particular, these three critical exponents, gamma, delta, tau, that control the demagnification, rotation, and time delay of successive images. And the photon rings converge to, you can see it here, but are distinct from, strictly speaking, from the critical curve, which would be, this infinitely thin line here. And they don't necessarily have the exact same shape, but obviously the shapes converge exponentially fast. Okay, so that's a summary of the theory. And now let me move on to the experimental proposal that I put forward with Sam Grella and Dan Moroney last year, which I think is an ambitious proposal in terms of the technology that we have today, but it's sort of the lowest hanging fruit in terms of the theoretical things you would want to measure. And I'm very curious to hear what your thoughts are. I know there are many experts in the audience, and I would love to discuss this at length. Everything I'm going to say in the last 5 remaining minutes is either in this paper or one of these two that discuss additional details. So very briefly, a radio interferometer measures the complex radio visibility, which is the Fourier transform of the image. And each telescope pair samples a point U in Fourier space, which is a baseline. It's the projected separation between the telescopes in units of the observation wavelength. And the key idea in the paper with Michael and friends is that if you go to very long baselines, which are long enough to have resolved the diameter of the ring, but not so long so as to have resolved its width. So if you're in this regime, then basically you should be dominated by a clean signature of the ring, at least in time averaged images where the noise from fluctuations goes away. And if that's the case, what you'll find is that there's a signal whose periodicity encodes the ring diameter. And this is the precise formula. This is the only formula that I'll only really involved formula that I'll show. So if you have an image which is of a narrow curve in the sky, if you go to this regime where you resolve the diameter of the curve, but you're not so far as to see the fact that this curve is not very thin, so you haven't resolved its width, then the complex visibility that your interferometer would pick up follows this form. And in particular, if you take the amplitude of this formula, you get a ringing signal where the periodicity is set by the projective diameter of the curve at the corresponding angle in the baseline plane. So that's the key idea. And so in particular, for M87, all we need to care about is the shape of an ellipse, which is a projected diameter that obeys this functional form. And let me know that the complex visibility is very hard to measure in its totality, because the visibility phase is subject to more noise, the visibility amplitude is more robust to it. It's easier to measure. And if you were to access only the visibility amplitude, then you'd be sensitive to the projective diameter only. So if we were to look at M87 on long baselines, long enough to pick out its photon ring, we expect that we'd see its projective diameter at every angle. And I'm about to tell you that it's that of an ellipse. So to summarize, what's the test? Can we test GR by measuring the photon ring shape? Well, there's two questions that need to be addressed. The first one is there a clean separation between astrophysics and GR? That is to say, between short and long baselines? Does that actually happen in realistic models? So could we test GR in principle if we had a perfect detector? And second, can we actually achieve the experimental precision required for an interesting test? That is, can we test GR in practice? So for the first question, there's a conclusive answer in the case of time averaged models, which is a big caveat that needs to be removed here. But in time averaged models of M87, the n=2 photon ring diameter can be measured from the interferometric signatures, and it is always that of an ellipse independent of the source model. So it follows this functional form. And is it possible to achieve this experimental precision in practice? I think there are many experts in this Zoom call that know more than I do about this. But based on a forecast that we did using some of the inputs that Dan Moroni gave us, we think the answer is yes. And we had a forecast model in which we forecasted a precision of a sub-percent level precision of this shape, and therefore of the strong field GR Kerr hypothesis. So to explain these 2 points is very complicated. I urge you to go look at the paper if you're interested, but very briefly, in one slide for each point. For the first point, all we did is look at many source models varying the spin of the black hole and the inclination angle. And so, of course, the radial dependence of the emission. We ray traced those models to get time averaged images that had profiles that look very similar to the ones we get from GRMHD simulations. We took the Fourier transform and looked at the visibility amplitude, made sure that on short baselines we fitted the EHD observations, which are shown here. This is 2017 data. And then we went to very long baselines and we checked that the ringing that we saw actually matched this functional form, which is predicted for narrow curves. And by fitting to this curve, we were able to find the periodicity, d phi, and we checked that d phi at every angle phi corresponded to the shape of an ellipse. And so we regard this as a prediction for M87. And then we said, okay, assuming some kind of precision that we hope would be achievable in our lifetime, according to Dan Moroni, we said, suppose we did the experiment and measured these kinds of data points, could we infer the shape of the photon ring from that? And it's a complicated subject, but at the end of the day, we were able to reconstruct the shape, the projected diameter at every angle. And of course, if you find the diameter of this curve experimentally, it either fits this functional form, and then if you have a successful fit, you can report that GR passes its test with the precision given by the RMS deviation, which for us was tiny. And if you cannot fit this functional form to the data, then you exclude GR at the associated p-value. And so I think I'll stop on this slide, which just shows the big picture. We want to test strong field GR with black hole imaging. So the cartoon, and I think a lot of work needs to be done to turn this into an actual robust mission design, but the cartoon is to have a satellite orbiting the Earth at a distance of about 300 gigalambda in baseline units, imaging the source, looking at the ringing signal that we get from the n=2 ring, and from that, trying to fit this projected diameter of an ellipse, which is the prediction from GR, and compare it to the data. Thank you.
Thanks for the really nice talk, Alex. We have time for a few questions. So again, please just raise your hand in the Zoom or go ahead and put them in the chat. So I see a couple questions in the chat. Maybe we'll start with that. I see one from Maciek who, well, maybe you want to just say it.
Yeah, sure. So I was just, I'm questioning the statement about this being totally matter independent. And my argument is that the family of photon rings really indicate that there is some stratification along
absolutely. So the fact that we don't have just so if we had a continuous emission region, we would expect to get just a flat, just a continuous logarithmic divergence in the image. The fact that instead of a log divergence, we get these stacked subrings, that particular structure follows from the assumption that there's a hole in the emission region. So I don't think it strictly has to be a thin disk. It can be a very puffy disk, and there are many people quantitatively right now, but I expect that as long as there's a hole in the emission, that you'll get the subring structure. But it's not completely matter independent. Of course, you also need optically thin emission, because if you have optically thick emission, then you don't have these light rays that go around multiple times. You just don't see the multiple lensed images. So it's not 100% matter independent, but I think the point is that the structure is there as long as you have an optically thin emission region. And then whether it's exactly the subring structure or a continuous profile, depends on the emission or not. And I think for 7, we think there is. But anyway, it would be amazing to see the structure, whether the holes are there or not. And then I think beyond that, you don't need too many more assumptions. So by matter independent, I mean, I should say maybe source independent. It doesn't really matter if, what the electron heating model is and so on and so forth. We don't have to argue about all these details, which are actually not really known for the true source.
Okay, we have a few more questions. Torben Frost asked whether you calculate the photon ring and other spacetimes than Kerr.
Hi, Torben. I have not. I mean, I think there's a paper by Sol Tucholsky and friends, one of his students, I forget her name, but I believe she did it for a black hole in de Sitter-Chern-Simons theory, which is interesting because it's a reasonable model for an alternative theory of gravity. And I think it would be interesting for more people to look at that. Absolutely. But I have not done it.
I see. Well, Frederick Vincent is on the call. I think has a paper on that, and Maciek and others. So if others on the call, have references, again, feel free to just drop them in the chat. And then I see a question from Valerio Boza, who says in a paper in 2008. Well, maybe do you want to ask your question?
Oh yes. So. In a paper in 2008, we studied the acoustic structure of Kerr lensing, and we showed that actually at each order n, you don't have a single image. You might have additional pairs of images, actually. So the structure is even more complicated going to higher order images. Have you explored this structure?
Yeah. And we've never talked, but actually I've read your papers, and that one in particular in detail. I think it's fascinating. Actually, with Torben, we tried to analytically reproduce these results, and we kind of gave up because it's so hard. And I think I agree with your comment. It's true. Let me just say that in the context of all these models that I've been describing, we're considering time averaged images. So we imagine sitting on the source for a long time, and the matter rotates. And so even if your source distribution is not initially axisymmetric, effectively by time averaging, you make it axisymmetric. And then I believe it is a correct statement that if you have a source ring, so an axisymmetric source, that will have a unique image labeled by n. So in other words, the theta orbit number n is a good label on source rings. But it's true that if you break axisymmetry and you look at single point sources, n is no longer a unique label for the images. And I believe it's possible to describe analytically this more complicated structure, and I hope to have results in that direction soon.
Thanks.
But yeah, it's very, very interesting.
Okay, I think we have time for one more quick question. Andrei Lyapunov.
Yeah, that's more of a comment. I think one should, in this calculation, first of all, I really like it because it's one of those predictions which are like clinical prediction. That's one you want to really test. And my word of caution, or maybe worrying for myself, is that if you just use essentially a couple of baselines with the different PAs, you might have a difficulty to weed out or distinguish between the contribution from the ring itself and from other structures in the source, which may act on the same spectral scale. So that's the 0.04%. I think you should want to try to see what predictions you would get with realistic foreground background of the source.
Yeah, so that's obviously, I mean, I had this caveat, which is we've assumed that we've time averaged long enough that all these fluctuations that could worry you, the ones that you're mentioning, are gone. Is how long in practice for these fluctuations to be entirely gone? And there are multiple people looking at this question. I think it's the obvious limiting factor in this experiment. And I completely agree with you. We should get answers to that by the end of the year. And actually, Zach Ellis, who's on this call, I believe, has been looking at very high resolution ray traced images of GRMHD. And so we have snapshot GRMHD images now that resolve the n=2 ring. And also you see this noise that you speak of on long baselines. And I think this would be a very interesting thing to discuss, but you can beat down the noise from the fluctuations and see the n=2 ring. But the problem is that if you can only measure visibility amplitude, so you don't average the complex visibility and then take the amplitude of the time averaged image, but rather take the amplitude of the snapshots and then time average that, those two things don't commute. And that seems harder to beat. It seems like a harder way to beat noise. So if we could measure, if we could do coherent space VLBI, that would be amazing on this time scale of months. Then, we'd be in business. And I think we need a little bit more ingenuity to understand what's the best way to beat down noise if we only have visibility amplitudes. But
you just ask the source to freeze. Tell them freeze. That's it.
Freeze.
Okay, sorry.
Well, so I'll just point out
It's very interesting.
We have a talk on Thursday that'll be on this coherent space VLBI concept.
Yeah, I would love to talk about it. But let me just say one last thing. I think this is a good tagline, which is this point here, that if the fluctuations are small, then this experiment should work and you could time average long enough to see this clean signature of the photon ring. And if the fluctuations are very strong, then they'll produce echoes. So you'll have random fluctuations and they themselves will be echoed because of these light rays that go around. And so then we should see autocorrelations in the data. And I think basically the structure that flows from gravity is there. The light rays do go around. There has to be a way to get it out of the data. And I think if the fluctuations are weak, the photon ring shape might be the best way to go. And if the fluctuations are strong, we just look at autocorrelations. And those also display, basically they have a very specific structure, which also encodes the critical components. And we've only begun to scratch the surface in this paper with Michael and Shahar Adar and George Wong. But I think there should be more work in that direction.
Okay, we do have to move on. Thanks again, Alex, for the really nice talk.
Thank you.
And for all the questions. Next, we have a presentation from Yu Suneto-san on linear and circular polarization images near black holes.
Okay, thank you for introduction. Hello, everyone. I am Yu Tsuneto, student from Kyoto University in Japan. Today, I will talk about my work, which consists of linear and circular polarization images near the black hole, based on these two papers. Okay, first of all, I will start by introducing our backgrounds and our targets. The plasmas accelerated and collimated from the active galactic nuclei have been observed and known as the agent jets since 20th century, but their driving mechanism has been an enigma for a long time. Historically, astronomers have suggested many theoretical models to understand the mechanism. For example, the Blandford-Zuniac process, where the spinning black hole drives the plasma jet through the magnetic fields. And to survey the magnetic fields configuration, potentially driving the jet, researchers have observed the polarized components of the jet at many wavelengths. In this context, the direct observation of the supermassive black hole in M87 by the Event Horizon Telescope, EHT, has opened a new era of the jet study. That is, now we can expect to directly survey the magnetic field structure near the black hole and the jet-based region by the EHT and other VLBI polarimetries. Based on such backgrounds, we think of predicting the polarization images theoretically to get information on the magnetic fields by comparison with actual observations and to shed some new lights on how the agent jets are driven. So our methodology to approach the radio polarization is by following two steps. In the first step, we need to construct models of the agent jets, for example, with root calculation or analytical ones. And here we adopt the GRMHD models provided by Nakamura et al., which we will see later in detail. In the second step, we implement the polarized radiative transfer based on the GRMHD models. And we calculate transfer equation of the polarization and construct images based on the models for various physical parameters. In this work, we especially focus on the CP components, which has not circular polarization CP components, which has not got as much attention as the linear polarization LP vectors. So now I will explain this basic transfer equation and physical processes involved in there. In the left side of equation, in the upper right, the integrand is the Stokes parameters, where I is total intensity, Q and U are linear polarization, LP, and V is circular polarization, CP. On the other side of equation, the first term is the four polarized emissivities of the synchrotron electrons, which is dominated by the LP components, while the CP component is weak at the synchrotron emission. And the transfer matrix in the second term, K, consists of coefficients for the synchrotron self-absorption, alpha, and the Faraday rotation of the LP vectors, rho V, and the Faraday conversion between LP and CP, represented by rho Q and rho U. And here we pay attention to the Faraday conversion process. This process becomes more effective in a region with higher temperature and stronger magnetic fields. So in energetic region near black hole, the CP can significantly increase to an extent comparable with LP components by the conversion processes. To put it the other way around, we can potentially survey the magnetic fields and plasma properties near the black hole through the circular polarimetry. Before we can proceed with our study, we have to introduce GRMHD models for our two targets, M87 star and Sage star. Nakamura et al. Performed axisymmetric GRMHD simulations and obtained strongly magnetized jets surrounded with helical magnetic fields, as you can see in the left picture. And here we take a black hole spin parameter of 0.9. And the GRMHD simulation gives temperatures only for protons. So we must determine the temperature of synchrotron electron through an assumption to calculate radiative transfer. And here we assumed the relation between proton and electron temperature based on the plasma beater introducing in a previous work. And in particular, we take parameters for M87 star, where the synchrotron electrons are typically cold in the disk region and hot in the jet region, as seen in the central panel, so that the emission from the jet region are dominant for M87 star. Meanwhile, in models for Sage star, we assume parameters where the electron are typically hot in both of the jet and the disk. And so the disk emission is dominant for such a star. And next, we will consider how the CP can be amplified. As seen in the last slide, there are hot electrons and strong magnetic fields near the black hole in our models. So the Faraday conversion rate becomes significant and becomes comparable with the Faraday rotation rate of the LP vectors. As a result, the linear polarization emissivity are shared with the circular polarization component through both the Faraday rotation and conversion processes. And the CP component, Stokes V, increases linearly as in the equation and the graph below. And these are the resultant images for M87 star. Here we took an inclination of 160 degrees, assuming a nearly Fresson observer below the equatorial plane. Total intensity image at 230 gigahertz is shown as color contour in the left figure. It gives an asymmetric crescent-like shadow of black hole because of the gravity of the black hole itself and the relativistic beaming by helical motion of the plasma. And at the same time, the jet feature is missing in the image due to the weak acceleration near the black hole. And these features are consistent with the EHT observation in 2017. And next, I will talk about our main topic, the CP image in the right figure. As described in the previous slide, the Faraday conversion occurs in the hot and strongly magnetized region near the black hole and changes the LPs to the CPs. In this case, the magnetic fields driving the jet is well ordered near the black hole, so the CP is uniformly amplified by the Faraday conversion process. Therefore, the resultant CP image is bright and uniformly positive in its sign around the photon link. In this way, we demonstrated that we can interpret the amplified and uniform CP image as a trace of the plasma and ordered magnetic fields near the black hole in M87 star. And next, we show the resultant images for Sagittarius star. Here we took an inclination of 30 degrees. Total intensity image is shown in the left figure, which gives a wide ring feature due to the broad emission region from the hot disk. And the CP image in the right figure shows the amplified components as seen in M87 star, but here they give a sign flipping feature in horizontal direction, consisting of positive components in the left side of the image and negative components in the right side, with a leftward vertical borderline or separatrix indicated by two arrows in the top and bottom of the image. And finally, the LP maps in the central figure shows bright feature along the separatrix in the CP image. In this way, we see the interesting features on both of the LP and CP images apparently involved with each other. So next, we will think of how these features are given. As described previously, here the CP components are amplified through the Faraday rotation and conversion process. Here we note that the Faraday rotation and therefore the circular polarization Stokes V are proportional to cosine theta b, where theta b is the angle between magnetic field and the line of sight. Therefore, the sign of the circular polarization component depends on whether theta b is acute or obtuse. In other words, whether theta b is smaller or larger than 90 degrees. Now, as seen in the picture, if we put an observer's screen in upper right in the slide, the angle theta b between toroidal magnetic field and the line of sight becomes acute in the left side of the screen, and it gives the positive CP components. On the other hand, it becomes obtuse in the right side of the screen, giving the negative CPs. And obviously, on the separatrix of the CP components, cosine theta b approaches to 0. So the Faraday rotation are weak along the separatrix, and the original LP components can survive from the Faraday rotation and depolarization, while the LP vectors are rotated and depolarized elsewhere. As a result, the LP fluxes are bright along the CP separatrix. In this way, we demonstrated for suggester that if we observe the sign flipping of the CP and the LP flux along the separatrix, we can attribute them to the existence of the toroidally dominated magnetic structure near the black hole. Now the question is why the CP separatrix appear in the left side, not the center of the image. And the answer is this is because of the relativistic effect by the disk rotation. If the disk was at rest, the separatrix would appear in the center of the image, as seen in the left figure. But actually, the disk near the black hole rotates in Keplerian-like motion. So as a result, the relationship between magnetic fields and the line of sight is modified by the relativistic aberration effect, as seen in the equation and the picture. So in this case, the CP components take negative values, even where these two vectors, magnetic fields and line of sight, are perpendicular with each other. So we can further conclude that the separatrix feature includes the information about the relativistic disk rotation near the black hole, in addition to the toroidally dominated magnetic fields. And next, we consider scattering effects in the interstellar medium, ISM. Suggester images in radio are known to be distorted by scattering in the ISM. And the scattering effects can be divided into two kinds of scattering. Diffractive scattering blurs the images, and the refractive scattering adds stochastic substructures to the image. So we implement these scattering effects into our images with two open libraries, Smiley and EHT imaging, and show the scattered image in the bottom. They give the polarization features described previously, the common separatrix feature in the LP and CP images. So we can say that these features survive from the ISM scattering effects. So finally, we show mock observational images to discuss the possibility to capture the polarization features in future observations. And here we convolve the image of M87 star and the scattered image suggester by Gaussian beam with a size of 70 microarc second, bearing in mind the angular resolution of the EHT at present and in near future, including Swiss VLBI. As seen in the figures in the bottom, we demonstrate that both of the CP ring in M87 star and the separatrix in suggester can be captured in future observations with high detectability of linear and circular polarimetry. And with all this being said, we have reached the end of my talk. I'll leave you with the summary of our project. Thank you very much for your attention.
Thank you very much for the really nice talk. Any questions? So is this something have you looked in how calibration errors might limit this? I mean, what do you think are the real observational prospects for M87, for instance? You know, usually it's pretty hard to do calibration better than an accuracy of about 1%.
So you ask.
Well, so when you generated, I'm just wondering if you think this is something that the EHT is likely to be able to measure. I see that it's about 2 orders of magnitude weaker than the image on, well, I guess the M87 circular polarization looks about 2 orders of magnitude less than the Sagittarius star circular polarization.
So you ask fractional polarization.
Yeah, the fractional circular polarization in the image. What?
After convolution, this M87's model gives about the linear polarization fraction of about 10 to 20% in locally, and of 1% after integrated over the image. So as a total flux.
And so that's linear, and what is the circular as a percentage?
About circular polarization, under 10% locally and less than 1% in total flux, total circular polarized flux.
I see. So this, just the image on the left, the bar says times 10 to the minus 7 at the top for M87. And for Sagittarius star, it's times 10 to the minus 5. Is that just because they have different pixel sizes, or do you predict that the M87 circular polarization is that much weaker? A factor of 100 weaker.
Sorry. It depends.
I don't know. Yeah, I'm just looking at, I'm not sure if you can see the annotations, but these two, these are the 2 numbers that I was looking at.
These two images has different pixels,
Okay. Yeah.
Construction. So it is, they cannot be compared directly.
Okay, that makes more sense. Great. Okay. Well, if there are no other questions, let's go ahead and move on. Thank you again, Suneto-san, for the very nice talk. And next, we'll hear from Andrei Bereshev about imaging of M87 and Sagittarius star with Milimetron. You're still muted, but we do see your screen just fine.
Good evening. Can you hear me?
Yep, perfect.
Okay, fine. My name is Andrei Bereshev, and I will present the work of the Milimetron team in preparation for the Milimetron Space Airfield BI operations. So the team is on the screen. So I would like to show this page as acknowledgements to Free Krylov, Heine Falke, Vladimir Kudryshov, and Sergei Lukács. And the outline of the talk will be the Milimetron mission introduction. I presume not everyone heard about it sufficiently. So the space airfield BI observations from elliptical orbit, as Milimetron is planning. I will talk about the 2D imaging and also about dynamics. And the space airfield BI observations from L2 orbits. And I will talk about imaging, which sounds a little bit contradictory that you can get any 2D imaging from L2 orbit because of the separation of the stations. But I will talk in detail why it is possible, and some conclusions and possible expansions on the Milimetron space mission. So Milimetron space mission is a mission of Russian Space Agency. It has a long history in making. It started even in the Soviet Union, but after successful completion of RadioAstron mission, who is undoubtedly familiar to everyone here, it is the latest space airfield BI mission, which has demonstrated that these observations are routinely possible. Milimetron tries to push these observations to a much shorter wavelength. And for that purpose, an observatory is being made with the mirror of aperture diameter of 10 meters. And that 10-meter diameter is stable now already for 10 years, because, you know, space missions tend to shrink the mirror diameter. So it works in submillimeter and millimeter range. It follows conceptually a successful RadioAstron concept. So that means it's not inflatable, nothing like that. It's just a classical deployable and adjustable antenna. I will talk about technology a little bit later. So antenna and focal plane instruments will be cryogenically cooled. We will use the advantage that we are in space below 10 Kelvin. So that means that we will get an excellent noise temperatures of an instrument, which will help the sensitivity a lot. So the orbit, which is very interesting for the single dish operation, there is a lot of push to get Milimetron around L2 Lagrange orbit, anti-solar Lagrange orbit, because of the stable thermal conditions in the stable orbit. But there is also a consideration to push at the second phase of Milimetron operations to elongated elliptical orbit around Earth, which is energetically pretty close, so you don't need a huge delta V in order to change this orbit. So launcher is Angara 5, lifetime goal is 10 years, and at least the cryo function for guaranteed for 3 years. So it will have two operation modes, space airfield BI, which actually can also be done from L2. The wavelength coverage I will talk in detail later, and the single dish mode, which will be done only from L2, which will utilize the cold telescope. The sensitivity 10 to the minus 22 watt square meter for spectroscopy, and 0.5 microjansky for photometry in a single dish mode. Well, space guys, the status of development of Milimetron, the spacecraft bus and instruments are in phase A, antenna is in phase B. The launch date is also now fixed and not really advancing to the end of this decennia, so 2029, 2030. So the more information you can get on the Milimetron.ru website, if you didn't visit it for some time, it has gotten a refresh, so it contains much more information at the moment, also in English. So it's led by PI Sergei Likhachov. Unfortunately, after Nikolai Kardashov has passed away, it has now been carried by Sergei Likhachov as Astrospace Center of Lebedev Physical Institute, who is the key organization of in Russia, which is behind development of this mission. So this is basically the poster of how the Milimetron would look like. So it is being launched by Angara Heavy. In stowed configuration here, it is stowed under the hood of this rocket, and it contains of the payload module, consists of the payload module and the spacecraft bus. Spacecraft bus will be based on Navigator concept module, which is the same module as was used successfully for the RadioAstron mission. Of course, with the navigation, with the modifications. For instance, the angular accuracy needs to be improved because it is a sub-millimeter wave antenna. So as you see, the Milimetron consists of the deployable antenna and then several layers of mylar shield and one inner shield, which is the cryogenic shield, which is connected directly to a cryocooler, and then the cooled container where the instruments are, and the warm container, instrument container at 300 Kelvin, where all auxiliary systems for instruments like spectrometers, data recorder, and so on is located. So this is the classical spacecraft scheme. The most important technology for now in Milimetron is its antenna. Again, it is not inflatable. So it is a deployable antenna consisted of 24 petals. As you see, the support truss on which you have, each petal consists of 3 panels, and the central solid dish of order of 3 meter diameter. So diameter is 8 meters, so it is a carbon fiber reinforced composite technology. And we have achieved here a specific mass, which is, of course, less, more than inflatable mirror, but much less than the classical solid mirror technologies. In comparison, as you see in the table, Milimetron is less at 8.5 kilograms per square meter if you launch this antenna. So these panels can be actually reproduced from a single mold. Each type of the panel is reproduced from a single mold, 24 times and plus for all kind of processes you need to launch the mission. This has been successfully demonstrated. In fact, there is a little factory built near Moscow, which is working already on this technology for a while, more than, say, 7 years. As you see, the mock-up of Milimetron, the engineering model has been made on the picture to the right, as well as calculations have been made. And this is the key. This is the mold on top and the replicated carbon fiber panel of the Milimetron mirror. And that shows a very good replication of order of 4.5 micron RMS. And it's not relative, it's an absolute number, RMS deviations. So that means that this antenna, if it's made of these panels and they are lined up in space, is suitable up to 2-3 terahertz operation, and definitely with the reserve will work at a lower frequencies, which I will be discussing today. So there is also, of course, a thermal design. This is the cutout of the Milimetron structure. This is where the instruments will be located. Instruments are in instrument accommodation study. So they are at the moment the boxes, but they will materialize pretty soon. And we have the cryo container, the cryo cooling system, and room temperature container. And here is the thermal model on the left shown, which allows to achieve the mirror temperature definitely below 20 Kelvin without a specific cooling of the mirror. And if one has enough resources, both money-wise and energy on board, then one can attempt to cool the main dish, and the main dish then, according to this thermal model, can reach the temperature below 10 Kelvin, which is very important for the single dish observations, but not extremely relevant for the VLBI receivers because they are all heterodyne, so they are quantum limited. Therefore, the noise temperatures will not be limited by the antenna temperature. Anyway, Milimetron instruments is in the plans for space VLBI receivers, which is relevant for this group. Milimetron heterodyne instrument, shortwave array camera spectrometer, which is a spectrometer like in Spica, and the long wave array camera spectrometer, which is more relevant for studying cosmic microwave background, which is part of this symposium as well, but of course not of this group. So let's concentrate on VLBI bands and channel bandwidths. So as you see, we cover 84 to 136 gigahertz, 211, 275. This is EHT classical band. Many observations are being done by EHT Event Horizon Telescope in this band. We also envisage that EHT will observe also at higher frequencies, and there are some pioneering observations already taking place. So the white selected bands are the high priority. What we also consider that these bands will be quasi-optically combined in one, such as the multi-frequency synthesis is possible. So that means the 3 frequencies, observing of three or more frequencies will be possible at the same time. That has been demonstrated to have a huge advantage to compensate for atmospheric phases and other variations. During VLBI sessions by our Korean colleagues, and there is a collaboration with Korean colleagues as well. So we have the classical heterodyne scheme for the receiver, as it's shown to the right. For 260 gigahertz channel, we will use SIS mixer, so that means it will only work for Kelvin. For the lower frequencies, we consider using high mobility electron gas transistors, and that is working also at elevated temperature. When the cooler fails, the Milimetron will still be able to do the VLBI observations, although with much higher noise temperatures. So to talk about the Milimetron space VLBI scientific tasks and constraints, so the major task is a high resolution 1D and 2D images of the black hole vicinity M87 Sagittarius A star or other sources which are suitable. Search for the wormhole signatures. So this is the focus. And 1D is specifically mentioned here because you will have a possibility to have from L2 very large baselines. And so there you will have only 1D capability if you use that very large baselines at this moment of the Milimetron located on orbit. So of course there are several constraints, such as sensitivity of a space telescope and the collaboration with the space ground baselines. So the collaboration is of course considered with EHT, Event Horizon Telescope, because it's a relevant bandwidth and relevant science. So we have onboard stable hydrogen clock, data downlink channel, and onboard memory of order of 100 terabytes. So that will be sufficient for observing with current bandwidth of order of 10 to 24 hours. But then you need roughly with the current data rate a month to downlink the data to Earth. It's still faster than getting the data from the South Pole in EHT. But yes, we are looking forward on the collaboration in deploying a faster data link. Of course, there will be tracking stations needed, and space ground VLBI geometry and space telescope orbit configuration and optimization, data processing and orbital accuracy, and many other tasks. So for addressing the science and how the Milimetron will observe, a Milimetron VLBI science working group has been created. The coordinator is Alexei Rudnitsky. So anyone who wants to join and interested in, say, influencing how Milimetron will observe and what, you are welcome to join these groups. So the sensitivity of the Milimetron high priority bands is shown here. Of course, the sensitivity for space Earth VLBI can only be considered as the pair of the ground station, and the ground station here is considered to be ALMA. And you see that with this, the sensitivity is pretty adequate to observe M87 or Sagittarius A. So let's talk about Milimetron space VLBI orbit geometry. So we are considering two orbits. One is the Sol L2 orbit. It's a classical L2 orbit. It's a wide halos around L2. From Earth, you would see plus minus 35 degrees above the horizon. Milimetron positions depending on where on orbit Milimetron is. So the orbital period is 178 days. The baseline is standard L2 1.5 kilometer maximum, and the minimum can be 1 centimeter or 1 meter. So I will be talking about that a little bit later in the talk. And then we are considering, and now the search is ongoing for the optimal orbit configuration that gives the moon gravity assist and a little bit of the delta V, which would be left after the L2 orbit existence. One can push the Milimetron on elongated elliptical orbit, which is very close. So the orbit we are considering is very close energetically to L2 with the periods of 10 days. So the baseline is up to 350,000 kilometers and maximum and 10,000 kilometers minimum. So it is actually not too far from the orbit of Radiostron, conceptually, elongated elliptical orbit. So this orbit we call the high elliptical orbit here in this presentation. So what UV coverages can be achieved? It of course depends on the particular implementation of orbit, launch date, and launch parameters. Therefore, one can influence this UV coverage quite a bit, and it should be optimized for the key sources one needs to observe. So, but one to the left is the typical orbit one can achieve for 1.5 days with the M87 high elliptical orbit observations. In the middle, the Sagittarius A star elliptical orbit UV coverage for 10 days, and for the same periods of time, similar periods of time, the UV coverage of Event Horizon Telescope on the right, simulated also for the reference. One can see that much larger UV baseline sizes are available from Milimetron, but as usual, the Space Airfield BI mission in this configuration suffers from rather sparse UV coverage. So from L2, in principle, one can achieve also rather compact UV coverage with the baselines, the space baselines going to be 1 Earth diameter or less, because if you align the Milimetron station in a line of sight connecting, say, ALMA and the Sagittarius A or M87, then UV projection becomes very small, while the W is very large. But since we are talking about a very small field of view, the large W doesn't influence a lot the imaging quality of Milimetron. So I will talk about it later. Here are the examples of what one can obtain as an image, as a 2D image, using a Milimetron orbit, elliptical orbit UV coverage. So we based ourselves on the model which we kindly received from Monika Mosi-Brodska. So this is referred to her publication in 2014, the model frames. There is also an independent model now exists in Athens Space Center. There is a theoretical group also busy with modeling of the event horizon. So to take into account the scattering, this model was Gaussian blurred. That's the second column. And then, for example, there is an EHT only image and the most right column is the EHT plus the Milimetron combination image for, I believe, 10 days, integrated over 10 days. And you can already see that the image quality for Sagittarius R is much better. Although Sagittarius R has been known to have a large variability, so therefore we will discuss it a little bit in a second. This also can be used for the dynamic imaging. So, but the most spectacular difference between EHT and Space Airfield BI and Milimetron could be observed if you model the M87. M87 is known as a less variable source. Therefore, all the integration are more plausible to converge to a very much nicer 2D image, and the picture says it all. As you see in the middle, the recovery of EHT, which was done by the Russian colleagues using the clean method, just from the model on the left, and with the same method, but the Milimetron UV coverage, the resolution can be improved drastically. I of course have to mention immediately that is all model dependent, so not the thorough analysis like was done for EHT. The images have been done by a lot of different models and so on. But this already shows you the power, what you can get from Milimetron elliptical orbit. So now talking about Sagittarius A is of course very interesting what happens with Sagittarius A on a short time frame. Here is a snapshot of UV coverage of Sagittarius A with EHT only and Milimetron with the different color. We show the baseline for 221 seconds, evolution of the baseline of for 221 seconds. And one can notice, if one can choose the part of elliptical orbit which has a very fast evolution, within this time frame you are able to evolve the UV coverage quite a bit, and that would allow you to enhance the UV coverage and obtain this type of snapshots here. So I will stop here for a little bit. These are the consecutive frames which are numbered here. To the left, this is the model from the same Mosibrodska et al. And in the middle, this is EHT only recovery with the UV coverage which was shown in the previous picture. And to the right is EHT plus Milimetron. Of course, you cannot see the nicely rotated image like the model, but you can already do quite a bit. For instance, you can calculate the center of mass, and there you can recover the center of mass location on the circle around, and this is the face. And the recovery of the center of mass is much more accurate than if you would recover the center of mass from event horizon only images. So in that sense, from the high elliptical orbit, even the dynamic images of Sagittarius A star in particular, if you optimize the orbit, becomes possible to a limited extent. So not talking about L2 orbit, again, if you optimize the L2 orbit such that the Milimetron is on the line of sight of your source, for instance, from Earth, or very close to the line of sight in the sky coordinates, then you can shorten UV coordinates to as short as the normal ones you observe with PHT. But then you have there, by choosing the right time in observations, you can have several Earth diameters, not necessarily many Earth diameters like the L2 location of Milimetron suggests. So here I show the UV coverage. I forget the label. On the left it is for the M87, and on the right it is for the Sagittarius A star. And this is unpublished data. So to consider that at least once a year, Milimetron will be able to achieve this desired combination to be on the line side of the required sources. It's at a different time of the year. This is a Molly-Wade map of the Milimetron orbit evolution for 3 years. This is L2, and the places where it gets close to the source, so that means that the baseline projection U and V becomes small, and especially this orbit has been optimized for M87. That happens once. For Sagittarius A star, it happens several times, but this orbit can be further optimized or even corrected to possibly realize M87, for instance, M84, and for instance, other sources can reach the same conditions for Milimetron, and this magenta traces corresponds to the size of 5, the baseline size of 5 Earth diameter. So observing from L2 with Milimetron using space Earth LBI is actually quite possible. And now, if one shows similar images, set of images, but now taking into account the UV coverage available from L2 orbit. So this is to the left the same model. Then EHT only that shows similar things. So the EHT only, we use now different recovery method, maximum entropy method, MEM. Sorry for the typo. And so the EHT Milimetron shows still quite a bit benefit in the spatial resolution, despite of the sparse orbit. So, and even if it will be decided to do L2 only, there'll still be very interesting experiment in order to do 2D images with Milimetron. Well, similar story about Sagittarius A, as you see here, and that is also confirmed with the fidelity and human independent way to calculate the image quality or correspondence of the model to the imaging. So
Andrei, 5 minutes left, including questions.
Yeah, so I'm almost done. So we also included atmospheric phase fluctuations. With atmospheric phase fluctuations, we had to use a fringe fitting in order to recover the image, but this appears to be possible. So we are also considered, just for the general information, that the best way to do the VLBI observations is to do space-space interferometer, and this is already a project of Roscosmos, where we consider to make several instances of Milimetron and located them on elliptical orbit, and this could recover at 650 gigahertz, where we assume that the scattering is the smallest. We can recover very nice images, 2D images, but this is of course very far in the future. And also in Russia, there are serious plans to build a new submillimeter telescope located near Uzbekistan as a possible station to collaborate for Event Horizon Telescope. So here are the conclusions. So Milimetron space missions is under development in Russia, and I hope I was able to convince you that it is actually pretty far in this development. The launch date in 2030. Significant progress has been reached in development of antenna technology and space VLBI technology. So Milimetron, hopefully convince you, will be very effective, both space VLBI from elliptical orbit and L2. Milimetron and plus EHT can perform dynamical images investigation from high elliptical orbit. I'm not talking about photon rings, we didn't consider them yet, but I think quite a lot can be looked in 1D mode, but also in 2D from Milimetron. And Milimetron plus EHT can perform efficient imaging from L2. That I hope I also convince you, because you can shorten the projection. And there is a conceptual study of cluster project. The name is Cluster Space-Space VLBI concept. I'm on many, for instance, Event Horizon Imager, one of the candidates, and now today I've heard about the inflatable version of that. And the new submillimeter station capable of submillimeter in Sufa, Uzbekistan, and Caucasus or Caucasus region is being considered also. Thank you very much.
Thanks so much for the very nice talk. Questions? So I see one from Alexander Sakharov.
Okay, do you hear me?
Yes.
In your talk, you noted that there is a hope to find wormholes. In this case, you should specify properties of wormholes which give you opportunity to distinguish such objects from black holes. Thank you.
Yes, unfortunately, the presentation was a bit short. So clearly, there should be a difference between a black hole and a wormhole. One of the major differences, as far as I'm aware, it has been studied in detail by Igor Novikov, just to refer to. So all detailed questions should be referred to him. But the main difference is the magnetic field. So the black hole must have a dipole magnetic field structure, and the wormhole can potentially have a monopole magnetic field structure, and that could be also a major difference, as well as the wormhole may have a source of light in the middle of the image. So that means that there are conditions that you get the light radiated from the wormhole itself, from the middle, not only the light orbiting around and various interaction with accretion and so on. These are the major effects which could be different, but it still requires rather careful modeling of this effect.
Okay, we're actually out of time, so I think we should move on. If you have any other questions for Andre, please just put them in the chat. And again, thanks for the very nice presentation. It's really exciting to see this come together. So the last talk that we'll hear today in this session is from Andrei Lyapunov, who will tell us about space VLBI studies of AGN, extreme physics at extreme baselines.
Thank you, Michael. Thank you for the inviting me to give this presentation. If it starts, is it not starting? So, I realize I'm just entering that age when you're invited to give some overview of historical events leading to modern situations. So this is, well, thank you for that as well. So this is what I'm going to tell. I'm going to try to get my sort of mostly personal view or impression of the space VLBI studies of AGN, and that's the starting from this illustration coming from Radio Astron. As you see, what you would see in the galaxy BLAC, hosting the BLAC object at about 900 million light years away. If you pointed Radio Astron at that and made an image, you see you could resolve, in fact, Sun and Alpha Centauri and even the Oort cloud very well. So this radio structure here, that's what we see there in this galaxy, and this is how the Sun and Alpha Centauri would have appeared if we could have detected them in at radio emission. So, without further ado, here's the some short summary of the space VLBI timeline. First proposed actually already in the 70s, soon after the first VLBI measurements were done. Partially a false hope, or some sort of a hope that you actually do not need increase the stability of the clock in order to get to a longer baseline. So anyway, this proposal was made already in the 70s, and space VLBI, unfortunately, since then has counted so far only 3 instruments and only 1 dedicated mission. Because this, if you look at these pictures from left to right, TDRS was just basically a proof of concept measurements made via commercial satellite, otherwise using for communications. VSOP was technically an engineering mission for the Japanese Space Agency, and the science program was a total add-on to so Radio Astron was the first and the only mission designed from the very, very beginning to be space VLBI, dedicated space VLBI mission. And what we have now is Milimetron, which Andrei Barashov just gave you a very nice introduction about, for which space VLBI or VLBI capability will be like not really an add-on, but an additional option to enhance the otherwise very busy program on a single dish. And there are, of course, many other space VLBI initiatives, just to give a historical overview. The KRT-30 of the Russian Soviet project, or a study, the Quasar, IVS, Alpha, all these 90s, 80s and 90s were sprouting with several initiatives. Then the VSOP came along and people were busy with VSOP, but Arise in 2000s and VSOP2, they consider the follow-up of VSOP, which potentially could have even included 2 satellites, was considered, but also dropped off by the Japanese and picked up by the, somewhat picked up by the Chinese agency with this NSVLBI project, which is also now on the back burner, and I'm not sure how far or how fast the things were progressing there. It's pretty much shut down or put in a freeze. Then some other discussions about the SUROs, about the low frequency interferometry, which also unfortunately did not go very far. And of course now, as you know, in connection to the successes of EHT, the idea is to bring the event horizon and black hole studies into the space. And there are 2 projects, EHI, Event Horizon Imager, and Black Hole Imager, which have been now considered, and I will talk about them later at the end of my talk. So this is what we are now, where we now, to 2030s, hopefully we'll get the Milimetron flying, and at some point later, most likely, or maybe also in 2030s, if we're very lucky, we may get one of those new missions ready to fly and to produce exciting results. So if we go back to the VSOP, this was, as I said, this, although engineering mission was the first really space VLBI observatory, which delivered a robust imaging at 1.6 and 5 gigahertz on baselines up to 3 Earth diameter, and it was really a good imaging instrument. If you look at the a picture of OJ287, OA36, made it with the VLBI at 1 and 5 gigahertz and VSOP at 1 and 5 gigahertz. You see, basically, you can get a very good imaging of the jet structures on scales of several hundred parsecs down to a resolution of about 4 parsecs. And that was a very nice instrument to study this plasma physics and jet physics, and also addressed many other scientific problems. There's a whole special issue in Proceedings of the Astronomical Society of Japan in 2006 dedicated to VSOP results or recast of the VSOP results. So you see it's 270 pages of very interesting papers about the results from VSOP. In partial, for instance, one of those exciting results is detection of this absorption associated with the accretion disk in the NGC 4261. There are a variety of studies which were enabled by VSOP. So after that, those new horizons that we got in Space Field BI, they came with the launch of Radio Astron in 2011, and we have this operations until 2019. So 8 years of successful operations and successful measurements and observations at 0.3, 1.65, and 22 gigahertz. Focusing on several key science programs, in fact, or key science projects. One of them is one of the most important results, probably legacy results from Radio Astron's AGN survey. There were 3 programs on AGN imaging, targeting the nearby strong and AGN polarization, nearby and strong AGN and AGN polarizations, altogether observing over 40 different AGNs for that purpose or for these purposes. There was very interesting programs on pulsars, masers, and general relativity tests or gravitational redshift measurements. Since I cannot just even try to summarize all of those, I just basically have to mention them. And then there are some results mentioned or described in recent paper by Nikolai Semyonovich by Kardashev in 2018. And that's the 5-year results from the Radio Astron mission. So imaging of AGN were mostly done during the perigee passages. You see this here in the middle, typical UV coverages with these dots in the center. This is ground baselines and some protrusions, 1 or 2, depending on how lucky you are. This is the tracks produced by Radio Astron Space Radio Telescope approaching or leaving the perigee. And sometimes you could observe at both phases. So you basically get to see 2 branches of that orbit. Otherwise, you would just be limited to one of those branches, and then UV coverage would be rather not really degenerate, but of course poor in terms of coverage of position angles. Nevertheless, the images were possible, and what is interesting also, you get set a lot of records in achieving different resolutions at different frequencies on different angular scales. So Radio Astron, as of now, hosts holds the records of the instrumental resolution, which is the Fourier spacings of 26 gigalambdas or angular scale of 8 microarc seconds. And this is the image of the maser, or the location of the maser spots in NGC 4258 at 22 gigahertz. You see this was achieved at a baseline of 340,000 kilometers. So this is the present record of instrumental resolution. Now, before going to the description of what Radio Astron have done with respect to the AGN imaging or AGN science, we just quickly recast the scales and physics, basic physics of what we are dealing with in this case. So this is a sketch of a typical AGN, radio loud AGN, where it's launched from the black hole. The jet is launched from the black hole, and then possibly or most likely dominated by electromagnetic energy, by Poynting flux, and that energy is converted at some point into kinetic flux. So that's where you start to see millimeter wave core, or some core of the jet at millimeter wavelengths, and then you see as typical manifestations of relativistic jets, as we know, superlunar knots, production of gamma to radio to gamma ray emission, instability shocks, and all of that zoo of interesting phenomena. What is most interesting at the moment from the jet science is how the jets actually launched, how the Poynting flux is converted into kinetic flux, and how it's the connection between jets, accretion disk, and the central black holes. And you see the angular resolution, or linear rather resolution, of different instruments with respect to M87, so linear scales in M87, and you see the radioastron really approaches the event horizon scales. But of course, at 22 gigahertz, you can be heard by scattering, and it can be heard by opacity. So in reality, this beam of radioastron resolution should be probably moved a bit further to the right, closer to the millimeter. Will be a millimeter wavelength core, and the HT, of course, can peer all the way down to the to the black hole. So what we're going to do here, or what we try to do with radioastron studies, is studies of brightness temperature, which allows us to address different questions about plasma and emission diagnostic, probe the inverse Compton limit, and see how the plasma actually gets cooled from inverse Compton to equipartition. And structure and magnetic field structure and total emission structure of the jet imaged with radioastron allows us basically to have a lot to say about the launching mechanism and whether the disk or the black hole actually play a more prominent role in launching the jets. So let me just start this short review of radioastron results with some presentation of the radioastron AGN survey, which is also a totally different or large topic, which cannot be covered in this talk. So the survey was targeted more than 230 different objects and measuring visibility amplitudes mostly at 1.65 and 22 gigahertz from baselines up to all the way up to 30 Earth diameters. There are many aspects of these studies of this database, many different correlations that are and will be studied and produced and investigated. What I want to briefly mention here is just basically the measurements of brightness temperature obtained from visibilities, which you can do by applying some assumptions to directly visibility measurements, and you can make a bracket between sort of minimum allowed brightness temperature and some characteristic or expected brightness temperature for resolved emission. So this is, the brackets are shown here on the diagram with blue color for minimum and limiting or characteristic temperature with red color. So you see most of them, or many of them, actually exceed the inverse Compton limit by quite far, by quite a margin, so almost like a factor of 50 or more. And that can be explained in many different scenarios. One of the most exciting scenarios, at least for me, is that this measurements, this extreme brightness temperature, can also imply extreme strong magnetic fields in case of some specific conditions which are feasible for runaway sail, feasible for Blanford's lag beam inside a Blanford pane. But what is interesting, these conditions which allow you to achieve such an enhancement of maximum brightness temperature by increasing magnetic field imply that magnetic fields can be actually higher than 10 or larger than 10 to stronger than 10 to 4 Gauss, whereas accretion disk and typical accretion disk black hole scenario supports magnetic fields up to roughly 10 to 4 Gauss. This is an interesting task to understand where such a high magnetic fields, if they're confirmed in these objects, can be produced, and that one potential way to distinguish actually between black holes, true black holes or canonical black holes, and some of their mimickers which do not have a true event horizon. So this is a continuation of this study, will certainly be interesting from variety points of view. So AGN imaging with radioastron. Now to these images, to the long promised images. So you see how you compare what you could obtain with the VSOP on the left-hand side for 0836 plus 710, and comparison what you get to see with radioastron. So even though it was difficult, you could basically make these perigee passages be used for the imaging experiment and achieve a 3 to 10 times better resolution compared to the VSOP resolution. Here for the radioastron, you see the ground array image in color, and counter show the actually respective radioastron image from the same, from the full data. And the beams are compared here on the left-hand side of these frames with orange oval showing the ground array image in the beam, and the blue dots or blue ellipse, in fact, in the center. This is the corresponding radioastron beam. And you see, you basically go all the way to essentially sub-parsec scales in a jet, which is at the redshift of 2.2. So this is an exceptionally good estimate, or exceptionally good way to look at the detailed structure of a flow on such a small scales in almost through a large part of the universe. And indeed, radioastron allowed us to do that also by setting records of angular resolution and breaking them and resetting them again. And this is the progression of these records, starting from that image of 0836, we had 30 microsecond resolution. And then image of BLAC was obtained at a resolution of 21 microseconds. And finally, that's probably going to be a final record for the radioastron imaging is the image of OJ27, which is has an angular resolution of 12 microarcseconds. So we basically get the very much detailed picture of the innermost jet on the flow in that object. And of course, just setting these records is not all what we've done. There's lots of things that's coming from this radioastron investigation, from radioastron imaging programs, and that's one of those examples that I want to show you. This is the 1.6 gigahertz radioastron image of one of the jet in the same object of 0836 plus 710. You see the ridgeline. You see how which structure you can actually get to observe and detect them with radioastron, and how you obtain the spectral index between radioastron observations at 1.6 and ground array image at 5 gigahertz. So you get a very nice and very well established spectral index image. So what we get from this analysis is that we see that the jet ridgeline really represents Kelvin-Holmes instability developing in the jet. And you can identify up to 4 different modes of this instability, which most important is helical surface mode, HS mode, which is actually developing slowly in the jet, but leads ultimately to its disruption. We see it actually in much larger scales, even with observation with Merlin. So we get good estimates of jet Mach number and the density ratio. So that allows us basically to investigate the jets with numerical simulations and more detailed modeling. And without radioastron, without this kind of ridgeline measurements, we wouldn't be able to get such an important input for this modeling. And spectral index, as what we see here, is that indeed a rapid shock dissipation. So the shocks are only present on small scales here. Of course, the linearly scales are quite large. It's a few hundred, almost 100 parsecs here for 5 milliseconds. But the dissipation is very pronounced. And afterwards, what you see in this jet are all effects of instabilities and pressure enhancements developed through the Kelvin-Holmes instabilities. When we go closer to the jet origin, to more nearby object like 3273, what we found with radioastron is a very interesting effect that we all know that jets are stratified, but typically we always assume that jets are, well, not assume, but actually see most of the time that jets are clearly or most likely edge brightened. And that's what we saw with radioastron at 1.6 gigahertz. If you look at the left panel, this is the contour image. That's what the 1.6 gigahertz image made with radioastron. But when we looked at the image obtained with radioastron 5 gigahertz, we see the clear sign of actually a spine brightening, because there's no way this central structure can be actually one of the sides, one of the limbs of the emission observed at 1.6 gigahertz. So this is well established. So if you just basically get the transverse profile and measure them along the large fraction of the jet and average them, this is what you get to see in the central panel. So the profile at 1.6 gigahertz is clearly like 2 humps, has 2 maxima, is limb brightened, and at the same time, the profile at 5 gigahertz is clearly just produces a spine brightening. So immediately what you see is that this spine should have optically thick spectral index, or be optically thick at several locations. And indeed, this is what you see if you take the spectral index or measure the spectral index in this jet. So this is a very important finding, which clearly shows this strong stratification. And for the first time, you can see the 2 frequencies, and you can really get the idea that the jet has to be really stratified, and we can try to get to model it. And what you can basically see that it's would be very much consistent if your flow is dominated by a poloidal magnetic field, but has a rather moderate particle and density gradients, which basically proportional to the distance from the jet axis to the power is 0.01, but 0.1, and it's enough if you consider these jet layers dominating the emission at 1.6 and 5 gigahertz. So that basically tells you that although the picture is quite unusual, the physics behind it is pretty much explainable. So there's no magic and nothing that very peculiar happens in that jet. So we should expect similar effects in more jets and in AGN. So, polarization structure in case of several sources, including 3CT45, was very interesting indicator for the development of magnetic field and development in shocks. So in 3CT45 in particular, if you look at this image at the left, where the ground array shown in colors again, and radio astronomy image shown in contours. So you see if you look at the region which you would call the core in the ground array, which is like a large blob here in the center, and you compare it with the contour image of the same region, you see an interesting picture which was already detected in VSOP observations. So basically, what you see as core in the ground, because of the resolution, is dominated by some component which is not really the origin of the jet, or optically thick end of the jet, as you see. And this core, in fact, if you observe it at the same frequency but at longer baselines, starts to break up into a really bright part, which is actually presents itself as a core for the ground array image. But also you see a slowly diminishing emission to the counterjet direction, or to the direction to the central engine, which is actually the true core. And if you look at the true core, well, I shouldn't say true core. It's just a jet. It's just a section of the jet which slowly turns optically thick at a given frequency. And you, in order to resolve that region, you actually need to get to a space baseline. So we could just see that what we would have otherwise identified as a core is actually a jet region in the jet, which is possibly just a strong shock. Whether it's standing shock or a moving shock, we do not know at this moment. But this is the polarization structure, which clearly indicates that the emission in 3CT45 on these scales up to the minus 4 milliarc seconds is dominated by shocks with the transverse magnetic field. So in this particular source, and we know that also from the previous observations, it's often that flares produce such very strong shocks which propagate downstream and dominate the emission for several years after a given flare. When you look at the more sort of not quieter source but less luminous source like BLAC, and you get a slightly different picture from the same polarization. BLAC is not known for such strong flares and regular flares which are produced in sources like 3CT45. And if you look at the magnetic field structure obtained from radio astronomy observations from that source, you see that on the right-hand side, you see that the jet is the polarization vectors change, and when we model that, the best explanation would be that the magnetic field responsible for producing this polarization is actually most likely has a helical structure. So that comes in line with the magnetically dominated outflow in this case, and formation of the flow dominated by magnetic processes. Another interesting thing is that we have brightness temperature measurements directly from the image, not just from the visibility, and we see the brightness temperature is clearly higher than 10 to 13 K and could be as high as some few factors of 10 to 14. And that's can be done to a great degree of certainty, because we get somewhat lucky with observing the BLAC, because you see this is on this visibility plot here, the ground array image continued with the visibilities measured on space baselines, but the orientation of the space baselines was such that you measure this upper envelope. You continue to measure this upper envelope in amplitudes, which means you basically measure, do not resolve the emission along the jet. across the jet, I'm sorry, you do not resolve the emission across the jet very much. So you get able to get these measurements all the way to large Earth separations with very good phase information. So you get a very nice assessment of the brightness temperature directly from the image as well. And finally, when we come very close to the core, this is when probably reaching a linear resolution of about 100 gravitational radii in 3C84. This is also a celebrated case. I'm sure most of you see these images, which are published in Nature. What you see here is the development of, again, a limb-brightened jet here. You probably need to get to a higher frequency, even higher than even 22 gigahertz for these objects in order to see whether there's something happening in the center or not. Whereas conditions could be such that in fact the emission in the center, if it's still dominated or dominated by Poynting flux, may be released even or generated only at the point when this Poynting flux energy starts to be converted into kinetic flux, and we do not know what's happening in the source. But what we do know is that if you look at the right panel, you see that the jet starts extremely wide, or seemingly, and then collimates also very, very rapidly. Either that, or the jet is actually here is anchored into accretion disk. So this is Blandford Payne part of the flow. And in this case, it could be quite possibly that what we see here is the Blandford Payne part of the jet, which is slower and generated from the accretion disk, but whereas Blandford-Snag part of it is simply not visible because of the deboosting, because of the viewing angle of the flow. So this is another example of the radioastron shedding a new light on an old and similarly familiar source, and also allowing to tell what is the relative prominence of different potential mechanisms of jet formation could be in this particular case, of course. So this is a few examples of the AGN studies or AGN imaging with radioastron. And of course, radioastron is now finished. We are working on the analysis of AGN survey data and finishing many projects on the imaging side. But the next decades of space VLBI seems to be dominated not by the sort of canonical jet studies. The results coming from the EHT raise a strong interest of black hole and event horizon science, and it starts to dominate also the present scope of space VLBI science or space VLBI projects or proposals for space VLBI. Andrei just told us about the Milimetron for VLBI, for which VLBI science will be probably add-on for the operation in L2, because it's going to be I guess simply a wonder if we detect visibility at 1.5 million kilometers, unless it's and in the projection or in a direction of the satellite, so the UV spacings will be much smaller. But at that one, it will be very interesting, but very again, it will be a little close to wonder if we detect correlated flux on the baselines of 1.5 million kilometers. So it'll be very interesting. Fringe spacings of a few nanoseconds, something which is we, of course, overturn our understanding of emission production in many sources. So, but nevertheless, I think despite our hopes, the visibility detection and tracking in L2 or photon ring science, as was described by Alex, would be probably the driving mode or the driving mode of operations for VLBI in L2, and we probably get some good imaging in quasi-radioastron mode before and after, or after these L2 operations on descending or ascending on orbits of the Milimetron. And there are, of course, now two different concepts produced and proposed for specifically for the event horizon studies. This is European Event Horizon Imager, which is a free fly concept of 3 space radio antennas on close orbits, which basically will slowly grow apart and then rejoin together on these close orbits and produce a quite dense UV coverage And the main targets for that would be Sagittarius star and M87, because you would need to orient this orbits in such a way that it would just optimize UV coverage. With just a few sources, you cannot reorient satellites easily. And then another concept is black hole imaging, which is produced on the American side, which is two or more space radio telescopes on low Earth orbit, so they actually fly on a fast UV feeding tracks, but provide moderate increasing of baseline lengths. But you can do multiple targets with these things. It remains to see which of these concepts or how successful they will be, and how they would actually compete with just simply providing a better dynamic range and better coverage, better phase stability for the ground array observation. But nevertheless, this is what the next decade or next decades are going to be bringing us from the point of view of new space VLBI endeavors. And that just brings me to my summary. So I wanted to say, to claim that space VLBI studies continuously break new grounds in astronomy, because they push the limits of angular resolution. And that's one of the parameters which is very important for uncovering new or shedding new lights on different astrophysical phenomena. Now we go to angular scales down to 8 microarc seconds, get the imaging resolution of the order of 10 microarc seconds, and Milimetron could push it by a tremendous order of magnitude if we are successful detecting visibilities on these tremendous baselines. So what we see from radioastron studies and from space VLBI studies, we see a repeated violation of the inverse Compton limit, potentially indicating the presence of ultra-strong magnetic fields, but of course there are also many other or several other competing explanations that can also bring such strong violations of inverse Compton limits. We have lots of examples when LGN imaging has provided very detailed accounts on various aspects of jet formation and propagation, and that's actually brings it to a point that imaging VLBI, space VLBI missions, even though they are not detected or directed at most of the hottest topics of the present day science, they may remain bread and butter instruments for many more mundane application of astrophysical studies of the astrophysical jets or AGN. So we have very good evidence for jets originating from the or part of the jet originating from the Blandford-Payne mechanism from the accretion disk, whereas detecting the Blandford-Snag component has been a bit difficult, not only for radioastron, but also for several other studies too, because it's either just not bright enough or deboosted for many targets where we can actually distinguish between the two components simply by achieving the sufficient transverse resolution. But again, next generation space VLBI missions such as Milimetron or proposed event horizon black hole images should push even further these limits if possible, and should provide us, bring new discoveries, and particularly, I would say, well, in cases, particularly in the areas of black hole physics, because all these three missions will be much better designed for working with this compact environment and small scales around the black holes, rather than providing a true imaging or enhanced imaging capabilities such as those of VSOP and to some extent of radioastron in the perigee imaging mode. So, thank you.
Thank you very much, Andre. So we're actually past time, but I think we have time for maybe just one quick question. Right.
Yeah, what is BHI? I Googled it and I saw something from 20 years ago, but I think it's a different thing.
That's on your side of the pond. This comes from Harvard, and that's basically what the idea is that you get the in order to get fast UV coverage for objects like Sagittarius star, for instance, you send several satellites on low Earth orbits. They're just few hours, or maybe not few hours, but very short orbits. And since there are two, or well, at least two, then the combinations of all these baselines will give you a very nice and very dense UV coverage. Of course, the maximum baselines will not increase with respect to the ground baselines, so your resolution will not be sort of increased by a large magnitude. So that's a long discussion. I guess we make it at the every time at many of those workshops. What are the trade-offs? Because in order to get the if you work with the, what's good about EHI, you can work at any frequency, even at those which do not cannot be observed from the Earth. If you come, because it's a free flyer concept, it has lots of other problems, has difficulties, but that is total freedom. You basically can select frequency, anything that you want. If you tie yourself to ground array, you tie yourself to frequencies or wavelengths which can be observed from the ground. You immediately get that thing. So then, if you want to again achieve some improvement, what you can do is just basically try to put this LEO satellites will give you fast UV coverage track for such a star. But then the question comes, because your baseline increase is so small, you can get the same effective resolution by simply improving dynamic range of the ground array observations alone. So that's a long discussion.
Okay, I think we need to close there, but thanks again everyone for joining, and especially to the speakers for these very nice presentations. And just a reminder that we'll have a second session on Thursday at the same time. So we hope you all can join us there as well. So thanks again, and hope to see you soon.
Thanks.
Thank you, bye.
Bye-bye.